Hello, everybody. I'm going to give a talk here, what I titled Scary Climate Change Calculations. Uh, so I recently did some calculations I thought I'd like to share with other people who might have had you know, misunderstandings or lack of understanding about climate change. I'd like to start off with a quote that I think is very appropriate. We do not inherit the earth from our ancestors. We borrow it from our children. And what we're doing right now is we're creating a future for all of those people that come after us. And it's a really scary future unless we try and change what we're doing. So I don't think we're giving our children the world they deserve. Okay, we need to do better. Now, if we had acted a few decades ago, probably 40 years ago even, when the alarms were sounded, we could have started more gradually and possibly been at a lot better place than we are now. But, it was a choice that really only the people of privilege could have made, and they were the only ones with the means to actually cause the problem, and they were also the only ones with the means to solve the problem. But the additional problem was, how do you give everything up, all this advantage that you have, when everybody's telling you it's a maybe? So it was pretty much easier to deny and ignore what we were being told. I was pretty unaware myself until probably the last many years, several years. But we face a really difficult problem now. Okay, so we have to really give up the way of life that we're living with using fossil fuels, or we'll not be able to heal the world, and we'll lose everything that has made the miracle of Earth. So in this presentation, I've tried to explain what climate change is doing to the Earth. I have tried to use simplified equations and calculations, and I use scientific explanations. But I try to show each step as best I can so that it's very transparent and you can see what I'm doing. I make my numbers ballpark numbers, one or two significant figures, so that it's as simple as possible. And I know that this approach will be too simple for some, but on the other hand, it'll be too challenging for others. So I'm sort of looking for a middle path through this. I want to be as thorough as I can, but I want to have a framework of simplicity that hopefully people can follow. Okay, for me, I believe it's worth the struggle to understand what's happening to our Earth. I hope you do too, but I have to warn you that some of the results are pretty scary. Also, the talk is pretty long, so I'll try to go fairly quickly, and if I'm going too quickly, maybe you can pause it and look over a slide a little more carefully than I'm giving it. So climate change and global warming, these are pretty famous phrases that have been around for a few decades. People have been telling us about it, and they strike a whole spectrum of responses from fear and alarm to annoyance and denial. Okay, so almost everybody who's heard these terms know that they are a result of too much greenhouse in the atmosphere. So there's a few greenhouse gases. I guess we might call them culprits. Most importantly is water, and then carbon dioxide and methane. These are the ones that are most famous, but there's other ones. But these aren't completely bad guys, because without them, the average temperature of our world would be really cold. Okay, minus 18 degrees Celsius or 0 degrees Fahrenheit. 0 degrees Fahrenheit is 32 degrees below zero. Okay, and it's hard to imagine a world where the average temperature is like that. It would be very harsh. Now, most of us agree that there's a real advantage to being at plus 15 degrees Celsius, or say closer to about 60 degrees Fahrenheit. Okay, that's a world that we can live in. It's conducive to growing food and surviving the world around us. So the problem is we progressed into what I would say is a danger zone. Okay, and there's not an easy way out. We just can't all of a sudden change our mind and say, oh, we didn't mean to do that. Okay, the stuff we put into the atmosphere, the carbon dioxide, will be there for hundreds to thousands of years, and it takes a long time for it to work its way back out. It's sort of in natural cycles. Methane, we're also increasing, but methane's it's much less than the carbon dioxide, but on the other hand, it's a much stronger greenhouse gas. So it's it's good on one side, not so good on the other side, and it's a real danger in terms of the potential being released from frozen Earth. Um, the thing with methane is it reacts with oxygen in the air, and it makes carbon dioxide, which isn't good where we are, but it's not as bad as methane. So the problem is nature, we keep adding methane. So even though it gets oxidized after about 10 or 20 years, we're constantly adding more in. Now nature does it naturally, but we do it purposely. Okay, so right now we're doing fracking in the United States and around the world. And when you frack, you're letting out natural gas, which is mostly methane. And there's a lot of incidents around the world that are not reported, where huge amounts are being blown out. Um, and so, we just have to be careful. Oil companies will tell you that it's a bridging fuel that is truly helping us in transition away from fossil fuels. But the fracking accidents are significant. So climate change is, of course, bigger than any of us. Okay, no one person's going to solve it. And in fact, no city can solve it, no state can solve it, no nation can solve it. This is a problem that confronts the entire world and requires the entire world solutions and cooperations. Now, unfortunately, humanity has had a problem with that, and it doesn't seem like there's a near-term solution, but we have to work towards that. There's no easy option, and only drastic action will save us now. So as they say, there is no planet B. So I want to look at this chart here just to give us an idea of what's been happening. So this chart shows, at least it gives a hint of the past few million years on Earth, we have not gone over what they call 300 parts per million. So that's a tiny little bit. Out of a million, there's only 300 parts of carbon dioxide in the atmosphere. Okay, that was for the longest time, for actually millions of years, in the atmosphere. Now that only happened after humans started burning fossil fuel, which would include coal, oil, natural gas. And this started big time around 1770, but you'll notice that it still is very slowly increasing, and it wasn't until recent times that we're really shooting up. So if we come over here and look on this side here, we see the parts per million of carbon dioxide. And so down here I've sort of indicated, for the last 10, 12,000 years, we were just running at the usual for the previous 2 or 3 million years, around 280 or so. There was a little up and down in there, but we never went over 300. So sometimes we go down to about 180, up to 280, down to 180, and so forth. Those cycles, we'll talk about those in a little bit. And so that went for a long time until about 12,000 years ago, human beings hit a climate sweet spot. Okay, we got at 280 and we've been staying there ever since. So that's kept our world warm, all right? Instead of going down to 180 where we had ice ages, we were staying right at 280, which is a comfortable Earth. Okay, and so then about 1770, James Watt invented that steam engine, and people started using fossil fuels for energy, and it really increased the possibilities and potential for human beings. So it was just incredible. It transformed our whole society to what we see today. But if we go back to around that time, around 1800, you can see we're right at around 280. Okay, that's going to be our starting point. And then 20 years later, we've only gone up 1 part per million. Okay, so that's so tiny. And then another 20 and another 20, and we've only gone up 1 part per million. But then it goes up a little higher. So here about 1880, that's another 20 years, 4 parts per million, and then 6 parts per million, and so forth. So we're creeping up, but still not huge jumps. Okay, we're still doing pretty good. 1960. Okay, some of us were actually alive in 1960, and we were only at 317. That's a workable number if we had stayed there. There were people back then telling us that this was a problem, but nobody was listening. 1980, we're getting up a little higher, 339. Now people are getting more alarmed. Notice we jumped up 22. And then between 1980 and 2000, we hit a special number, 350. And that was a number that people felt like things would be okay if we could stay below 350. That was around 1987, but we didn't. So there's actually a website called 350.org, which is concerned about climate change. You can check it out if you want. And then after 2000, we kept going up more and more. And so we're at about 2020 right now. And last year we added in about 40, or the last 20 years, we added in about 45 parts per million. So it doesn't look like we're slowing down. Okay, we're at a level that people think are dangerous, and we're going every 20 years, 45 parts per million. So we don't know the future, so I just kept using that number, 45, 45, 45, 45. In reality, if we don't change, we're probably going to be more than 45 the next 20 years, and then possibly more than 45, and that would put us at even higher numbers. But if you look down here at 2100, which is an artificial cutoff, we're not going to stop at 2100, but if we look down here at 2100, we would be about 600 parts per million if we don't change anything and just hold steady. We're probably going to go more though. So this is big time trouble, really big time trouble. The Earth wouldn't be the way we think of it now. So we don't know what's going to happen, but we hope that we can bring this back down, maybe approach these numbers over here. Now the other guy that's a biggie is carbon dioxide. So notice a big difference in the scale. These are in hundreds of parts per million, so 300, 400. If we come over at methane, we're in just parts per million, 1 part per million, 2 parts per million. So you think, oh wow, that's a lot better than 400, okay, 1 or 2. Methane also started up low, and we've been adding a little bit to that. But remember, it doesn't stick around real long because it reacts with oxygen to form carbon dioxide. But we keep adding in more, as you can see right here, because there's more people and there's more things that we're doing, more domestic animals, cattle, there's more rice, there's more fracking wells. So we're adding methane all the time here. Now there's another problem here, and that is if we warm up the world too much, there's a lot of organic matter that's frozen in the earth, permafrost and peat and things like that. And if we get up 2-3 degrees, that stuff could melt, and we could get a huge burst of methane out, and that would greatly accelerate the global warming, and then we would be in big trouble. This shows the temperature for the past, this is a couple thousand years right here, but the temperature doesn't change much even if we go back even, say, 2 million years. There's a little up and down from what we call the Milankovitch cycles, but they've always been there. We've been pretty comfortable for, like I said, for about 12,000 years, what I call the climate sweet spot, and that's where humans have really taken off to become the society that we see today around the world. All the advanced technology and everything, and ability to grow food and so forth came in this 12,000 year period. Okay, so you see it's pretty flat here, actually going down a tiny bit. There's only a couple tenths of a degree here. But then all of a sudden right here, when we hit that time of James Watt and his steam engine, you'll notice the temperature takes off. Okay, it's zooming up, and it's not stopping. The temperature's sort of lagging what's going to actually happen. We'll probably go a little higher even. Okay, this part right here where it's zooming is actually expanded over here, so you can see the more rough flow of the curve. Okay, it's up and down because they're just natural, events of weather and stuff where it goes up and down. But climate is different. Climate is more predictable than the weather. But you see there's a lot of uncertainty in these points. These data points here show the measurement of trying to take the temperature of the planet Earth. That's a really hard thing to do, okay? But they got people out there working on that, okay? And if we don't stop this, we're in big trouble, okay? Now the people who are doing this is not easy. This is hard work, okay? So we have scientists and engineers who have devoted their entire lives to the pursuit of telling us what is happening and what we need to do. And we can't tell these people, you're frauds, you're telling us fake news and stuff like that. They are trying to protect our lives. We can go back hundreds of millions of years, billions of years, and we can see what's happening to the planet Earth right now. Okay, and it's because of these people that we can do that. So the thing about science is it might not always be right, exactly right on the first try, but science constantly challenges itself and corrects itself and works its way towards factual information. And we need that information to make better choices that will save our lives, save the lives of future people, rather than ignore them at our own peril. The fake news isn't the scientists. The fake news is the politicians telling you there's no problem. And so we have to take control. Now this is sort of at the heart of our problem, and that is we have an exploding population. It makes everything harder because we have more and more people going after fewer and fewer resources. But it wasn't always this way. Humans, like I said, about 12,000 years we hit that climate sweet spot. But we have been around a long time before that. Humans started out maybe 200, 300,000 years ago, at least the form of Homo sapiens that we are. And then they went along pretty flat subsistence living, barely surviving. And then they hit a real bad spot there in about 75,000 years ago, when they think a whole series of volcanoes went off in, I think it was Indonesia, the Toba volcanoes that went off. And it put out so much sulfur oxide and dirt and dust in the atmosphere that it made sort of a volcanic winter for 2 or 3 years, cut down on the light getting into the earth, and the food resources were diminished, and so a lot of living organisms had a real hard time there. It's thought that the human population went down to maybe 3 to 10,000 humans, so we almost were wiped out. But from that start, we began from that, and there was like an ice age in the middle there. It got really cold, and then it went up. But about 12,000 years ago, we hit this sweet spot. But even then, you'll notice, we still haven't got up to 14 million till 3000 BC. So for the 12,000 to 3,000, we were less than this, starting at maybe 10,000 and increasing. But we're still staying pretty low, and we're talking the entire planet of the Earth. Okay, it wasn't until, let's go back 2000 BC, well, 4000 BC, that's when Judaism started, around there. 2000 BC is when Judaism started. About 0 BC is when Christianity started. About 1300 is when Islam started. And so if you look at the populations then, here's about 0 BC, about 200 million people on Earth. And then we're going up to some place in between here, 1,000, 1,500. We still were less than 500 million people on Earth. And actually there's a real bad spot in here in the 14th century, about 1350. They had the bubonic plague that wiped out maybe 30-40% of Europeans, and actually around the world they had the bubonic plague. But we didn't get to 1 billion until 1820. Okay, all the time before that, it took us to get to 1 billion. But after that, we took off. So the next billion only came in about 127 years. And then the next billion, what is that, about 33 years. The next billion, 15 years. The next billion, 12 years. And so you can see what's happening is the population is shooting up. There's a lot of reasons for that. Until science came along, which is about 300 or 400 years ago, people were just subsistence living. Okay, you were just scraping out a living from year to year. There was a lot of disease. Most babies died. Maybe 30-40% of babies died less than 5 years old. Women died in childbirth. There were plagues, so forth. But people started figuring things out, so we had better nutrition, better sanitation, better healthful ways. That we had medicines, the vaccines and antibiotics that prevented the mass epidemics that they had. We had better education. People started learning things about the world. Mortality rates went down, and that's why we started increasing. These are all good things, and really we owe a lot of this to science. And so again, there's another reason not to demonize our scientists. They are helping us. Okay. Now the problem is, here we are at around 2020 or so. We're almost to 8 billion. I think we're at 7.7 billion, and we're not slowing down. So they're figuring by 1250 or so we might be at 9 or 10 billion, probably maybe a little less than 9 billion, hopefully. But if we keep going to 2100, we might hit 10 or 11 billion. And the Earth is just having a hard time. We use too many resources per person in the rich countries to do this for the entire world at that level of people. Okay, so this is a problem we're going to have to control. And birth control doesn't really work. People try to force women to do stuff. That's like the recipe for increased population growth. What we have to do is we have to give women the opportunity to make choices of their own and be educated and understand how to improve their lives. That is the way we will control the population. So I have here, it all begins with energy after that little introduction. And so I put here what is kind of like our little energy unit that we're going to use throughout these talks. This is a tiny little cube right here. It's about the size of a sugar cube. Okay, and if this was water, it would be 1 gram of water, or it would be 1 cubic centimeter of water, or it would be 1 milliliter of water. These are all different ways of saying the same thing, but it's pretty small. Think of a sugar cube. That's our energy reference. Now, if we warm that 1 degree Celsius, which is 1.8 degrees Fahrenheit, which is 1 degree Kelvin, so you notice Kelvin and Celsius are the same, that would be what we call 1 calorie. So the first guys doing this, that's the way they did it. They measured in calories. But we have a more modern unit, which is called joules. So joules uses like units in physics, kilograms, meters, seconds, and things like that, to do the same thing in a more quantitative scientific way. So that's what we're going to use. We're going to use joules. Now, if I had 1,000 of anything, then we put a kilo in front of it. So we would say kilojoules or kilocalories. Now, you are familiar with kilocalories because that's a food calorie. So when you eat a food calorie, that's you're eating 1,000 little tiny calories. We just lump them all in together. So if I had 1,000 calories, that would be a kilocalorie. If I had a kilocalorie, that would be 4.2 kilojoules. If I had 4.2 kilojoules, I'd have 4,200 joules. Okay? So we have these different kinds of units. People use them calories for food and joules for scientific work. So let's just take a look at something pretty familiar. Say we have a cup of water. We'll say a cup of water is 8 ounces. And we want to figure out how much energy it takes to bring this up to a boil so that we can have some coffee or tea. Okay? So I'll assume that we start at 25 degrees and then we heat it up to 100 degrees where it's boiling and we can make our tea or coffee. Now we need to all, notice up here in the units, where are they? The units are in kilograms or grams, and so we're going to have to change this. Oh, I'm sorry, over here. 1 gram of water is our unit of energy. So we're going to need how many grams we have. And in an ounce, there's 28.3 grams. Okay, times 8 of them, so we have 226 grams. We have to take each one of those grams, and we have to heat each one of them 75 degrees. So we have to multiply these guys together for our little energy unit up here to see how many of those we have. And so when we calculate it out, if we were the old-fashioned way, we'd say almost 17,000 little calories. That would be like 17 kilocalories. But if we convert it to our unit that we want, 4.2 joules per calorie, we would have 71,000 joules, which would be 71 kilocalories. Okay, so again, we're going to mostly work in joules throughout here. I just wanted to show those energy units. Now, another problem that we have for ourselves is we have 3 commonly used temperature scales, so it's a little confusing, but 2 of them are pretty closely related. It's not a problem. It's mainly America that has the Fahrenheit scale over here, so we have to include that one too for those of us in America who like to think in Fahrenheit. Okay, so let's start with the Celsius right here. So Celsius has 2 special spots. One is at 100 degrees, and that's where water boils. And one is at 0 degrees, and that's where water freezes. Because water is such an important liquid in our world. Okay, and so this was kind of a reference point for the early scientists. And then they divided everything up into 100 units between those two. So pretty logical. Water freezes, water boils, that's 100 degrees. Now if we come over and look at the Fahrenheit scale, what we see is that that has different units. These are not so logical. So for the Fahrenheit scale, if we were at 100 degrees Celsius, we would be at 212. So a lot of Americans would say, oh, that's where water boils, 212. And if we were freezing water at 0 over here, we'd come over and for a freezing point of water, we'd say that's 32 degrees Fahrenheit. So if you take the difference here, that's 180 degrees. And if we take the difference here, it's 100 degrees. So a Fahrenheit degree, a Celsius degree is about 2 degrees Fahrenheit, 1.8 more exactly. Okay, so we can go back and forth and convert between these two. And so a lot of times I'll list both types of temperatures because there's different ways of thinking about it, and not everybody's going to think the same way. If we come over and look at this scale, this was a scale that people figured out after they got more familiar with science. Okay, it turned out that there was a bottom point here. There's a point down here where we cannot go below that temperature in our universe. That's called 0 degrees, absolute 0. And this scale is called the Kelvin scale. Okay, so its units are exactly the same as the Celsius, but it just has a different starting point. So this one starts at 0, and sometimes in scientific equations we have to use this equation. These other ones won't work. But over here we would be at minus 273 degrees Celsius. And if you look over here, that would be like minus 459 degrees Fahrenheit. For people who use the Fahrenheit scale, this is like off the chart, unbelievable. Anything could be that cold. Anyway, so we have these three scales. I just put them here to show you what they are. Now, the thing about our world is until we came along with fossil fuels, the whole world had to live off of the energy from the sun. So every day the sun would come up and shine and would dump its energy down into our world and give us the energy for life. But it was sort of a set amount. It's a paycheck that the sun gave us every day. And from that paycheck, we could support all the life that could be supported on Earth. So we had the primary producers like plants and plankton. And they absorbed that energy from the sun, and then other animals took advantage of it all the way up to the top predators, what we call the apex predators. Okay, but that meant there was some serious competition for that energy. Okay, and that resulted in life and death battles and outcomes for that energy. So I have here just three, XYZ life forms. They're taking their total energy, and then all of a sudden X and Y get much more efficient at collecting that energy. And so as they get more efficient, if they take, say, half of the energy of Z each, then there's no energy left for Z. And so Z is done. Okay, Z would go extinct and die out. Because the only energy we have is the energy we collect from the sun, every day. Now, so for hundreds of years we lived this way. The primary producers, the plants and the plankton, they collected that energy. Now they took the carbon dioxide and water that was in the world, and the thing that made them so valuable is they could take light and use that light to convert these guys into oxygen and carbohydrates, carbohydrates being the food that we eat. The oxygen at first was a disaster, because when this started first happening, there were only microbes and animals living in the ocean. And so it was a disaster, wiped out tremendous amounts of microorganisms. But the guys who figured out how to live with the oxygen got a really valuable tool, because the oxygen combining with carbohydrates and fats generates a lot of energy that larger organisms can use to, say, move around and live their life. Okay, so in each level, say somebody would eat the plants, and then somebody would eat the animal that ate the plants, and all the way up at each level there would be somebody below you and somebody above you, until you get to the very top, what we call the apex predators. So at each point you're going to lose a little bit of the energy, because the guy above you has to support its life, moving around, metabolizing, and living, but also reproducing. And then there might be somebody above you that takes advantage of you until you get to the top. And so the number of animals at each level goes down, down, down. At the top, there's a lot fewer apex predators. And so this is actually a problem in our world today, because humans are pretty good at killing off these guys, because they're too good of competitors against us, and we want everything for humanity when we really need to share it a little more. But the problem is they provide a downward pressure sort of to keep everybody in competition and have life be as efficient as possible. And if we take that away, then you can get explosions of populations that overwhelm the earth. So here we have our producers. We have animals that eat them, and then the bird eats the grasshopper, the snake eats the bird, the owl eats the snake, and so forth. And all of these guys will die. And when they die, they start to break down. And so we have organisms that decompose them, and they make the nutrients and starting point for the primary producers. And so here we have that circle of life that the Lion King tells us about. Okay, so it is really a little circle there. Now, so our energy, where does it come from? Well, it comes from the sun. Probably over 99% of our energy. And it's made from fusion reactions that are going on in the core of the sun, mostly hydrogen going to helium, but there's a few other things that are happening too. So that converts the energy, the mass of the hydrogen, when it gets transferred and fused into helium, into energy. And so we have that famous equation, E equals mc squared. And c is a huge number. That's like 3 times 10 to the 8th meters per second. And when you square that, you get this humongous amount of energy out of a tiny little bit of mass. And so down in the core of the sun, it's making 3 times 10 to the 26 joules every second. So remember, joule was our unit, and we don't even know what 10 to the 26 is. It's such a humongous number. But it's so big that they figured at the core of the sun it's about 15 million degrees Kelvin. Okay, that's our absolute temperature scale. Now the temperature doesn't just pop out at the surface. They estimate that it takes about 100,000 years for that energy to work its way out to the surface. And by the time it gets to the surface, the temperature of the sun is about 5,800 degrees Kelvin. Okay, still pretty doggone hot, but of course not the temperature of the core. Now, it turns out that we have a law called the Stefan Boltzman Law, which can calculate the amount of energy leaving any object that is warm. They call it black body energy. Now, if an object is not completely efficient as a black body, it doesn't give off that absolute amount. It's called a gray body. It gives off a little less. But we're just going to assume everything in our calculation here is a black body perfectly giving off all of its energy. Okay, so the Stefan Boltzman Law can tell us what that energy is. So if we look out on the surface of the sun, we said the surface is about 5,800 degrees. And if we come down and look at the Stefan Boltzman Law, Stefan Boltzman Law says all the energy at all the wavelengths that are possible for the energy is equal to the simple little constant right here. Not so simple, there's some terms inside of it that we're not going to look at, times temperature to the fourth. So look at, that's pretty significant. Temperature to the fourth power. You're multiplying it by itself 4 times. So that's going to be a really big number. Now the Stefan Boltzmann constant is a really tiny number. It's 5.7 times 10 to the minus 8 watts. Remember, a watt is a joule per second. Okay, and remember, a joule was just our tiny little amount of energy from our little sugar cube size amount of water. Okay, so watt per meter squared per temperature Kelvin to the fourth. And then we're going to multiply times that temperature of the black body to the fourth power. And so we'll come out with amount of energy per square meter. So if you look at the temperature to the fourth, canceled temperature to the fourth. And we get watts per square meter. Now square meter is pretty tiny. Meter's around 3 feet. So this is about 3 feet by 3 feet, just a little tiny bit. But if we calculate this for the sun, it's mind-boggling. Okay, so we calculate, it comes out 6.4 times 10 to the 7th watts per square meter. That tiny little 3 by 3 over here. 6.4 times 10 to the 7th is 64 million watts. That's joules per second per square meter. And that's every square meter on the sun. So how many square meters are there on the sun? Well, the sun has a diameter of 1.4 times 10 to the 6 kilometers. Remember, kilos 1,000. So if we make that meters, which is what we're trying to do over here, we multiply by 10 to the third, so we have 1.4 times 10 to the ninth. The radius of the sun then would be half of that, 7 times 10 to the eighth, and the area would be 4 pi r squared. So that would come out 6 times 10 to the 18th square meters. Every square meter, 10 to the 18th of them, would be putting out 64 million watts. That's mind-boggling, okay? So that energy is coming out in all directions, all sides of the sun. Now, how does this affect the Earth? Well, the Earth's sitting way out here, about 93, 94 million miles away. And so we're going to get this one little sliver of the sun's energy heading towards us, and it's going to hit the Earth. By the time it gets to the Earth, it's estimated that energy has dropped down to about 1,370 watts, joules per second, per square meter of the surface of the Earth. Okay, but the Earth, half of the Earth's surface is behind the sun, and so that'll just be in dark. We won't be hitting that, and so we're going to lose half of this amount. And then at the angle that it hits, it's not straight on. The straight on energy is coming in at this level, but at the poles it's going to be a lot less. So that's like cutting it another half. And so if you take a half times a half, that comes out to about a fourth of the actual energy that's reaching the Earth is going to enter into the Earth environment. Okay, so that would give us about 340 watts. That's joules per second per square meter. Now another factor is that when it comes into the Earth's atmosphere, it doesn't all reach the Earth's environment. Only about 70% does. Okay, because part of it is reflected by the atmosphere and part of it is reflected at the surface of the Earth. So 30% is reflected out. We don't get that energy. And that reflection is called albedo. So any object that reflects some of its energy is going to reduce the amount here that we actually see. So now we could come down and we could calculate a temperature from this, because we know the energy and we have that Stefan Boltzmann equation. So we're looking at 340 or so, but we have to multiply by 0.7. If we do that, we get about 240 watts, joule per second, per square meter, and that's going to equal sigma, which we know. That's the Stefan Boltzmann. Oh, I forgot a minus charge there, a minus on the exponent, times temperature to the fourth. So the temperature to the fourth is what we're solving for. So we take the Stefan Boltzman constant over to the other side and divide, and that's going to give us a really big number because this should be 10 to the minus 8. And so we get 4.2 times 10 to the ninth Kelvin to the fourth. We have to take the fourth power of this, which you could do on a calculator, but I already did it, and that comes out to be 255 degrees Kelvin, okay, based on 30% of the sun's energy being reflected and reducing it to a fourth of the energy reaching the surface of the Earth. Okay, now that's no greenhouse effect. Okay, we haven't really talked about it, but the gases that we have in our atmosphere, carbon dioxide, water, and methane, actually absorb some of this energy and make our effective temperature on Earth higher. So if we took the actual temperature of Earth, put in our little Earth thermometer, we have those all over the Earth, thousands of them, then we would get an average temperature for Earth of 288. So that's quite a bit warmer than this. In fact, if you come down and look at this, this is the difference between comfortable and unlivable. 255 Kelvin is minus 18 Celsius. That's the 0 degrees Fahrenheit that I mentioned earlier. That's no greenhouse effect. With our greenhouse effect, we're up here at 288 Kelvin, which is about 60 degrees Fahrenheit. So when we solve up here for, no, that should be a sigma, we come up with about 392 for our 288. So we substitute in 288 degrees Kelvin, and we get a 392 watts, that's joules per second per square meter, which is a lot higher than we've set up here at 240. Okay, but that's because we're bouncing the energy around over and over with our greenhouse gases. Okay, so here's my little schematic of this. We have the sun up here shining, putting out at 64 million watts per square meter. But by the time it gets to the Earth, we've reduced it to about 1370 times 1/4, so that's about 1340. As the energy comes in, and the sun's putting it out as visible light. Okay, that's why we can see the sun. It's burning very, very hot, and that requires a lot higher energy light, which is visible. But when it gets here, the clouds will reflect some, and then at the surface, wherever the surface is white, so like we have snow and glaciers, the North Pole, the South Pole, any place like that that can reflect, that's going to reflect some too. And so the combination of these reflect back out about 100 of our watts. And so that reduces our watt total to about 240 over here that we're absorbing. Okay, so we don't get this. That's the 30% lost. Now the part that gets down here to the surface, it's going to heat up every part of the surface to higher temperatures. It's going to convert this visible energy, visible light, into a low energy form of light, which we call infrared, IR. And so we'll have a lot of IR, which is heat, coming off at the surface of the Earth. All right. So that IR is excites the carbon dioxide and water to higher levels, and then those transfer their energy to the other molecules of the atmosphere that don't interact with IR and spread that energy around. Okay. So some of the energy from the sun that makes it in is absorbed by the atmosphere. Okay, molecules in the atmosphere, and some of it's absorbed at the surface of the Earth. So I have here 77 watts in the atmosphere, 163 watts at the surface of the Earth. Okay, and like I said, the IR gets excited, then it gives off its energy to other molecules, kinetic energy, and so it transfers it around. The energy emitted from the Earth is considered about 398, so I'd say around 400 watts per square meter, from transferring it back and forth, back and forth. We'll take a look at a little bit more of that later. And so about 358, 360 will be absorbed by the atmosphere. Some of that is bounced back because it's going in all random directions, front and back, left and right, up and down. Some of it that keeps going up will actually escape the atmosphere from these points up here, so we'll lose energy from the atmosphere. And some of it, where it's in the clouds, that will be reflected up as well. And if you add all this up, it comes out that we're putting out about 240 at the same time that we're getting in about 240. So there's a kind of a balance there, an equilibrium. And that's kind of based on the amount of greenhouse gases that we have here. If we change this, then that will change the amount of energy we give out or absorb. Okay, so remember, watt, joule per second. And then every square meter So on Earth, I calculated that out to be about 5 times 10 to the 14th square meters. So if you take that little bit of energy, which is pretty tiny, but you multiply it by 5 times 10 to the 14th, and that's a lot of energy that we have on the Earth to live. I thought it might be good to look at the other planets, the rock planets, rocky planets. So we have Mercury, about 36 million. It gets a lot more energy. You see here we are at 1370. And then we reduce that by a fourth. And then we have that albedo, the part that's reflected. For Mercury, there's not much there to reflect. It absorbs almost everything, about 90%. So we're going to get most of its energy. And it doesn't really have an atmosphere, so there's almost no greenhouse effect. So if you look at the predicted temperature, 435, and the observed temperature, they're almost the same. Okay, very little, but very hot, as you would expect, because it's close to the sun. Now, if we come to Mercury, Mercury is a lot farther away, 68 million miles away, so it has lower energy reaching it. We take 1/4 of that, we get 662 watts per square meter, but we're only going to multiply this one by 25%, 0.25, because Mercury is surrounded by clouds. Those clouds are clouds of carbon dioxide, about 95%. And so that carbon dioxide is going to reflect a lot of the light out, but it also has a humongous greenhouse effect from all that carbon dioxide. And so it's predicted to be about 232, which is less than Mercury. That's what you would expect. And minus 41 degrees Celsius, so this would be unlivable. But it turns it around with all the carbon dioxide, bounces that energy around inside until it increases up to about 735 Kelvin. It's actually hotter than Mercury, even though it's many tens of millions of miles farther away. That would be the equivalent of 462 Celsius. Okay, remember 100 degrees Celsius, water is boiling. So at this temperature, you could actually melt solid lead, convert it into liquid. So a tremendous greenhouse effect. They call it a runaway greenhouse effect. And people sometimes alarmingly say that could happen to Earth, but if that does happen, it would not be for probably over 1 to 1.5 billion years for that to happen. Right now, we're coming in at 1370 times 1/4. We take 0.7 of that, that's actually absorbed into the Earth's environment, and that predicts a temperature of 255. But we just saw that Earth's temperature is actually 288 degrees Kelvin, and that's because of our greenhouse gases, water and carbon dioxide, and a little bit of methane. If we went out one more planet beyond, which is also a rocky planet, Mars, we're at 144 million. It's getting less energy, as we expect. As you get farther and farther away, the energy gets more dilute. We take 1/4 of that. Now Mars has an albedo of about 0.25, pretty close to us, 0.3. So Mars is going to absorb about 0.75 of its energy, and that would predict a very slight increase. It has almost no greenhouse gases because its atmosphere is so thin, but a tiny little bit of effect. So, but it's running about the same, very, very cold, far too cold for our world, minus 58 degrees Celsius. So I actually did the calculation here for the ideal case of Venus. You can take a look at that, see if I did it right, using the Stefan Boltzman Law. Okay. Now, I'm just looking at these two right now as black bodies. We already talked about the sun, and the energy it's putting out is very high and strong. That's visible light. It also puts out other energy to the side. We'll talk about that in a minute. But visible light is the #1 energy form coming from the sun, and that reaches us on Earth, but now greatly reduced. And so the energy that we put out as a black body is heat. It's infrared. Now, we couldn't see that with our eyes, but we could certainly feel it. If you open a car on a really hot day and you get blasted with all that heat coming out, that's basically you're getting an IR blast, but it doesn't damage you. It's just a little bit hot. Okay, so each solar body is, in the ideal sense, a black body. They're usually not perfect, but pretty close. And we can use the Stefan Boltzman Law to look at temperature, and we can use the Stefan Boltzman Law to look at energy. We'll do it both ways. Okay, so here's the sun. This is what it would put out with its 5,800 Kelvin, and these are tens of millions. Okay, 90 million, 80 million, 70 million. Here's 64. That was the average amount coming out from the sun. Now, if we look at where that shows up in what's called the electromagnetic spectrum, visible light is one little part that we're most familiar with. Okay, because we see, and that's a really big And the reason we see is because we live in the world of the sun, and we've evolved to detect that energy. Fortunately, this energy is not so strong that it breaks the types of bonds that we are built of, or else we couldn't exist, because we'd be blown to smithereens if the energy could break our bonds. But there is an energy beyond that that's a little bit higher. That's ultra, beyond the violet. The visible, usually people are familiar with this: red, orange, yellow, green, blue, indigo, violet. And if we go beyond the violet, we can't see it, but it's there, and it's very powerful energy that can break bonds that we're made of. And so that's why we have to be careful. And if we go down below the red, infra, below the red, that would be IR, and that's where the Earth is going to put out its energy. And if we went below that, there would be the microwaves. And we're all familiar with microwaves because of the ovens that we have nowadays that we can cook food with. Those weren't actually available when I was a kid, but they're very convenient. Okay, now I put here just a little line to show the amount of energy coming out from the Earth and its IR. We couldn't even see this. Remember, this is tens of millions. But I took this little scale right here and I made a different graph, a plot. But this is only tens of watts. Remember, joule per second. So the amount here is so tiny it wouldn't even show up on this chart over here. But this is what the Earth is putting out. Okay, so we're putting out our maximum amount of energy as IR, maybe a little bit on the edges here. Okay, and we can calculate that again with the Stefan Boltzman Law. So sun, 64 million watts per square meter, Earth, 240 watts per square meter. Now I want to take a little bit of a look at this electromagnetic spectrum. Okay, we would think of the visible light as the spectrum, but all of the electromagnetic radiation is a spectrum. So we're familiar with a lot of these. Visible light, because we see, is right here, and then beyond that is the ultraviolet. So I put over here a little scale in kilocalories and kilojoules. So kilojoules, remember, that's 1,000 joules. And so if we're sitting up here at, say, 630 kilojoules, that would be ultraviolet light, part of it. It's a little window here. And then we look at the bonds that we're made of. So here's like a CH bond. It's about over 400 kilojoules, but we're putting out almost 600 kilojoules. This is enough energy to break this bond. And it's enough energy to break this bond, and it's enough energy to break this bond. And if we start breaking these bonds, then that means our biological molecules are falling apart. We would die. We would have problems. And so they tell you stay out of the sun at noon because there's a little bit higher incidence of ultraviolet. Fortunately, we have something protecting us out in the stratosphere, which we'll talk about in just a minute. A little bit lower energy, 50, and down a little bit and up a little bit, so around 50 plus or minus kcals, or around 200 plus or minus kilojoules. So we're looking at different kind of energy. It's a lot less. If we have a really weak bond, like a bromine bond, it's about 200. Bromine bond can be broken. In fact, they do that experimentally on purpose. They use light to break that bond. We have a particular pi bond. Notice how there's two lines here, double bond. And one of those bonds can break if it absorbs about 60 kcals, or about 250 kilojoules. And if that happens, then that's what allows us to see. So we'll talk about that on the next slide. And then down here in infrared, notice how low we've gotten, 10 kcals, 40 kilojoules. So this is definitely not going to hurt any bond, but what it does is it takes bonds and it makes them vibrate more and bend more. And so that's where it puts the energy in. And those little changes turn out to be really significant. That is what's warming our world, is these vibrations and these bendings of these bonds and these polar bonds. Okay, non-polar bonds don't really interact with IR, and that's the bulk of our atmosphere, but the polar bonds do. We'll look at that. And then if we even went down to microwaves, now we know microwaves can do something because we put food in there and it cooks. So even though the energy here is incredibly tiny, 0.08 kilojoules, okay, what is that? That's like 80 joules. That's so tiny. But what it does is it makes the water molecules tumble around and spin, and as they do, they bang into the food molecules, and they keep doing it over and over because we keep pouring in the microwaves until the button stops, until we turn it off. And so that's what causes the transfer of energy, and that's what's happening in IR. So in the microwave, we're just doing it to a very small sample of food, but in the Earth, the IR is doing it to the entire surface of the Earth. Okay? So this would be the ultraviolet. Say we have oxygen. Over here is our Earth. Above us, right above us, is what they call the troposphere. That's maybe 7 miles wide. And then if we go up above that, they have the stratosphere, and that goes up to maybe 31, 32 miles. And there's other layers out here that I'm not showing. But in the stratosphere, some of the oxygen that gets up there gets changed by the very reactive, energetic ultraviolet that's coming in. So the ultraviolet that comes in is damaging, and it splits the oxygen molecule into two oxygen atoms. One of those oxygen atoms grabs onto an oxygen molecule, okay, in its desperation, since it's unstable, and makes what we call ozone, puts three of them together. So what that did was that took that ultraviolet photon away from reaching the surface of the Earth, and that protected us, because we don't want this to happen to our molecules. Now another thing is, once we make this, it itself absorbs another type of ultraviolet photon and protects us again. Okay, so this ozone is crucial to our survival up in the stratosphere. On the other hand, it's extremely reactive, and if we had ozone down at the surface, it can destroy biological molecules. It can attack them and break bonds and stuff. So we don't really want ozone down here, but we need ozone up here in the stratosphere. Okay, so down in the troposphere, ozone is a pollutant. Now the visible light is a lot lower energy, and so I drew this complicated molecule. I know not everybody's going to understand this, but this bond right here is the crucial bond. And notice this is a really big giant part, and this is a really big giant part. And notice how they're bent towards each other. So these groups are really crowding each other. It's unstable. And so the body will tie this whole molecule to a protein, and then when the visible light comes in, we don't need much energy to break this bond because of all this crowding that's here. And so it will take the pi bond, the second bond, and it will split those electrons apart. And then that allows this thing to rotate. And when it rotates, the big parts will rotate far apart, as we see, and that will trigger an impulse from our cells to the visual cortex, and allow us to see. So we get that impulse to the brain. Okay, when it's over here in this form, they call this 11 cis retinal. And when it changes over to its other form, recombine those two, it's called 11 trans retinal. And then the body will recycle this back over here. We'll do it over and over so that we can see continuously. So this visible light is really useful, but it's not going to damage us. It actually helps us. Now down in the infrared, we're at very, very low energies now. And it's going to be special types of bonds. So notice here I say polar bonds. Polar bonds are have opposite charge connected together, sort of like little magnets. So one part will be sort of negative. Oxygen likes to collect electrons and be negative and pull them away from other guys that are left as positive. So we have something like carbon dioxide, which has these polar bonds and can interact with the light. Water has oxygen connected to hydrogen, which is also very polar. It's a bent molecule. This one's kind of linear straight, but it can bend. So when the IR gets absorbed, carbon dioxide can bend, or these bonds can stretch asymmetrically. One's a little short, one's a little long. And so those interactions absorb the IR, and then that excited molecule gives that energy back off, transfers it to the Earth's environment. Okay, and that can happen for the water too. We can actually take spectra of this, and we can see where those places are. So water can absorb in certain regions, and carbon dioxide can absorb in certain regions. And we actually use that to identify things in chemistry. I even went down below to microwaves because we'll look at a little example of that. So microwaves are even smaller. Say we come down another 100-fold or so, and the energy that we're putting out here causes simple little water molecules to bounce around, and so they can go spin on their top, and they can rotate, and they can bang into other things, and they constantly do it. When they bang into something, they transfer their energy and become relaxed into ground state, but then they get re-excited, and then they do it again and again. And so as long as you have that microwave on, you're exciting those molecules to transfer their energy to the food molecules until you get to a point where you have cooked what you want to cook. Okay, so the big deal for each of these types of spectroscopy, the UV, the visible, the IR, the microwaves, is that they start off in a comfortable spot, which we call the ground state. Then we put in some energy that matches this energy gap right here, and we make those molecules jump up to this higher energy state, which we call an excited state. And then the molecule interacts with its environment and transfers its energy back out to the environment and goes back to its ground state. And so at this state right here, it's over here, it could get excited again if we keep dumping in energy, which we do with, say, sunlight, or which we do with microwaves. We keep dumping in energy. And so we excite, relax, excite, relax, excite, relax. And each cycle we're transferring energy out. Okay, so for IR, the big ones are carbon dioxide. So you can see the little cycle that it goes through here, ground state, excited state. Water goes through this little equilibrium here, and methane goes through this little equilibrium here. We could measure all the different places where that happens if we looked at sort of like a prism with visible light. You know, you can show all the different colors that are there. So if we go across here, there's a lot of places where water, carbon dioxide, and methane can interact with the IR radiation. But we don't need to look at every little specific band there. Okay, but that's where it's picking up its energy. So I have what I call the 5-minute climate change experiment. This is something, when I was thinking about climate change, how could we show that really easily, show the significance of what climate change is doing? So anyway, I thought I'd try this out. I got a bag of popcorn and I put it in a microwave. Well, the microwave is only about 1/100th the energy of IR. So that's really tiny energy. IR is tiny energy compared to visible light. Okay, so it doesn't seem like we're really putting in a lot of energy here. But all of us know, all of us have done it for sure, is we've overcooked something. So microwaves can do some serious damage. Okay, so that low amount of energy, even though it's low, causes these water molecules to continually transfer their energy over and over and over to the food molecules until we get to the point where we're happy, where we have the food at exactly the point we want to eat it. So I stuck my popcorn bag in for like 1.5 minutes because that comes out just the way I like it. And so it looked like this right here. And then I put in another popcorn bag. I added 1 minute. I didn't even double the time. I just added 1 minute because I know since I messed it up before. And this is what came out. So notice how black and charred it is. And these things are actually stuck together. Okay, and it smelled so bad when I opened the door, and it let out so much steam and stuff that I had to take it outside and open the bag and just let it air out for a while. And in fact, it stunk up the house for about 2 hours. So this kind of shows that even though you have a tiny amount of energy that you're talking about, it can do serious damage. This was not even double the time. This was only 1 more minute. And I don't suggest you go over 1 more minute, because at some point you could actually maybe catch it on fire. You don't want to do that. So this is a profound experiment. This is an experiment you can do, and that will tell you how climate change is working, what we are doing to our Earth. Now on Earth we might be heating it up 1 degree, but remember that is like joules per square meter. Remember, we had 10 to the 14th square meters on Earth. And so we have that same amount of energy spread around uncountable amounts of time. And so 1 degree is really a huge amount of energy, as we'll see. So what I did here was I wanted to look back at the history. Earth's history actually goes back 4.5 billion years. And there's all kinds of things that have happened. Life didn't actually crawl out of the ocean until about 4 billion years ago. But I'm just going to go back about 400,000 years, because we're mainly concerned with what's going on with people. So if we go back about 400,000 years, we could see carbon dioxide, we can see the history of that, we can see temperature in degrees Celsius, we can see sea level, and we can see this because of those scientists that are helping us. Okay, so this really gets my ire up, because those scientists have helped us see what's going on and what's going to happen. And we have people out there denigrating them, okay, slandering them, making fun of them. We need to be thanking these guys. Anyway, let's go back here. So you'll notice that carbon dioxide is going down and up and down and up and down and up. And then if we look at temperature is going down and up and down and up and down and up. And then we look at sea level, it's going down and up and down and up and down and up. So there's these cycles. Okay, so there's reasons for these cycles. They aren't all due to carbon dioxide. We'll look in just a bit at Milankovitch cycles. That's the main reason. But if we go across here for the last 400,000 years, you'll notice that in carbon dioxide, we never went above 300 parts per million. And in fact, we could go back a couple million years and not really go above 300 parts per million. Okay, 300 parts per million is really a high amount for our recent history of the Earth. And whenever we're up here, they call it an interglacial warm period. It's a comfortable place to be. Okay, and if you look at where people actually got started, so remember, about 70,000 years, we just barely made it out of those volcanic eruptions. But about 12,000 years, we hit what I call a climate sweet spot. Okay? And so we've been here for about 12,000 years, and this is what has allowed us the very comfortable living, where we're not just subsistence living, barely surviving, very comfortable living that allows us to become who we are. Okay, but notice right here, it's just a dot on this little chart here. That's where carbon dioxide started shooting up. Okay, so right now we're about 415, and we haven't seen that for millions of years. Okay, we are super high. When you see that 415, it's not quite the same, but think of Venus. Okay, Venus is 95%. This is hardly anything, but it is a significant amount that can affect our world. Now, what does that do? There's temperature over here. So temperature is going down and up and kind of paralleling the carbon dioxide. When the temperature goes down, it gets really cold. Notice the number of degrees here. This is not a huge amount of degrees. This isn't like you're talking about the Arctic temperature in the middle of winter. This is the average temperature of Earth. And so we've only gone down, 4 or 5 degrees, and we reach these cold spaces right here, which we call ice ages. And so in these ice ages, that's a significant amount of ice. Okay, it's like glaciers that are 2 miles thick, and they extend all the way down to New York in the United States, or they extend down to Europe. Okay, so these are really cold times. And then somehow we come out of it. Okay, the temperature somehow gets warmer, and as it does, we get more carbon dioxide, and down and up. And so if you look at these cycles, they're on long times, tens of thousands of years. So 400,000, 300,000 for, say, a cycle, say 100,000 years. And so it's going up and down. So again, once we hit this certain level right here, we were at a comfortable spot around 280, and that lasted for 12,000 years, and that's where we have developed. Now, if you look at sea level following this, of course, if the temperature is higher, the ice melts. Okay, and so we have some reference point for sea level. Now, if we start taking all that water and freezing it because it's getting so cold, we're making a really, really giant ice cube, then the amount of water goes down. And around the Earth, it could be significant. So this is minus 300 feet. But then it melts and it comes back up. So we're going up and down in sea level. Now, in the world that we're talking about here, that wasn't a big deal because there were no cities, there were no roads, there was just Earth. And if we're changing, notice it's changing over maybe 50,000 years here, then animals and plants and everything have a chance to adapt and to change their living style, or perhaps create a new species that's better able to survive. Some are going to be lost to extinction, but some will adapt. And so animals had a chance here. Okay, so if you look over here, what we're doing is we're shooting everything up super fast, including temperature, but it's a very tiny scale right here. We're shooting up temperature, right here, really fast, and then it takes a long time for the water to ice and water to adjust to those changes in temperature. They don't change right away. Just think of a pot of water on a stove. You turn up the fire, it doesn't instantly boil. Okay, there's a lag time there. It takes a long time. Or you put ice into the water into the freezer, it doesn't instantly freeze. There's a lag time. So even though temperature is changing, carbon dioxide levels are changing, we're slowly seeing the sea level change. We'll look at that in a little while. Now, the main reason for these things are called the Milankovitch cycles, and we have 3 of them that we'll talk about. So I've grossly exaggerated this ellipse. It's not really this bad. But here's the sun and here's the Earth. So the Earth's going around the sun, and the Earth goes back and forth between elliptical orbit, which is just sort of elliptical, and then sort of a better circle back and forth. But you can see on the ellipse, the way I have it drawn, so sometimes we're farther away, and the Earth's going to be colder in these times, and so over here it gets about a little closer, perhaps about the same. And then if we're more symmetrical, where it's more circle-like, we have a more even climate instead of more extreme. And these cycles right here go back and forth around 100,000 years. It's pretty complicated because these cycles change because of gravitational pull of the other objects in our universe, or in our solar system. So planets like Jupiter, the Sun, Saturn, they all are at different times, different closenesses to the Earth, and so that's going to affect this. So it's kind of complicated. But again, notice very long, 100,000 year cycles we're talking about. There's another little change that Earth has. It's not straight up and down. It's tilted a little bit towards the sun. So say this is the North Pole, and the tilt is anywhere between 22 and 24, 25 degrees. And right now we're kind of right in the middle, about 23. But as it tilts more towards the sun, then you get more exposure at the poles, and so you get a better chance that it's going to be warmer, that the ice might melt. But if it tilts up further away, more straight up, then it doesn't get as much sunlight at the poles. There's more chance that you'll have ice there. And so that could change things too, and that's about on a 40,000 year cycle. And then the Earth also has a wobble because it's spinning like a top. So if you ever spun a top on the table or on the ground, you'll notice it kind of precesses around. And that's going to change the angle to the sun also, and that's about a 20,000 year cycle. So this is kind of complicated. That's all those up and downs I was talking about before. So I just made up a little plot here. I made it sort of ideal as best I could. So I have the elliptical cycle, 100,000 years. So this would be back 100,000, then 200,000, and so forth. So that's down and up and down and up and down and up. So we're closer when it's warmer. We're actually more elliptical when more circular when it's warmer, and more elliptical when it's colder. Up and down. And on top of this, we have the tilt of the Earth going about 22, 25 degrees back and forth. So it's getting colder and warmer and colder and warmer. And then on top of that, we have the precession of the wobble, spinning like a top, and that's faster. And so you can see there's going to be times where these maybe cancel each other and times where they add together. So like the way I have it drawn here, this is warmer and this is colder. They cancel out a little bit. And then times where maybe they all add together, and that would be even warmer. So we have a whole possibility of temperatures that are here. But these change on very slow time scales, tens of thousands of years. What we're doing right now is we're changing on about 100 to 200 years. Okay, way, way faster than what's happened geologically, historically. Okay, now one thing about the carbon dioxide, remember that kind of followed the Milankovitch cycles. When the Milankovitch cycles make everything a little warmer, then the oceans are going to be warmer. And a lot of the carbon dioxide is dissolved in the oceans. So if the Earth gets warmer, then that carbon dioxide can come out of the water into the atmosphere and start to heat up like it does as a greenhouse gas. And you can just use a can of soda pop as your analogy here. Just think of a soda pop sitting out in the open on a table on a hot day. You don't really go over there and pop that thing open right away because the carbon dioxide comes blasting out of the can. Okay, sometimes explosively, and you can spray it all over. On the other hand, if you take that can and you put it in a really cold refrigerator, okay, and then you pop it open, then there's hardly a little blip because it's so cold the carbon dioxide is staying in the water. So when the Earth is really cold, carbon dioxide stays in the ocean more, it's more soluble, and that takes it away from the atmosphere, which means we don't have as much greenhouse effect, which means the Earth is colder. And when the Milankovitch cycles make everything warmer, it releases the carbon dioxide to the atmosphere, which induces the greenhouse effect, which makes everything warmer. And so they kind of follow each other. So what is this atmosphere we're talking about? Well, the atmosphere, they divide it up and say is 1 million parts. Now, most of that is nitrogen. Okay, so nitrogen is a very simple molecule, 2 nitrogen atoms connected. They have no dipole moment, so they are not IR active. And that's about 78% of our atmosphere. Now, that nitrogen is crucial because all the nitrogen inside of us ultimately gets taken out of the air by organisms that make our food for us. And then about 21% is oxygen. Oxygen's kind of like nitrogen. Oxygen at both ends. It's not IR active, but we got a lot of it. And then next we have argon. So argon is just an inert gas. There's only one atom. Of course, it cannot have a dipole moment. So none of these guys are IR active. They're not going to absorb that IR energy coming off at the surface of the Earth. They're just blah. They just sit there. They're actually bouncing around in the atmosphere. But you can see that is the bulk of our atmosphere. Okay, that is the bulk of our atmosphere. Now we also have water. Water is all over the place because it could be at a very dry desert where it's almost zero, or it could be really right next to the ocean where the temperature is pretty high and there's a lot of water in the atmosphere. And so it could be really high, say 10,000 parts per million in some places, 0 in others. I wrote 2,000, just kind of an average value for the water. Now the water is polar and bent, and it's very IR active, so it's very good at absorbing that IR energy. Now when we go to carbon dioxide, notice it drops down. It's at 415, sounds pretty low, but remember, for last few millions of years, we've been running at 280, okay, for about 12,000 years. This has been the ideal place. As we put in more carbon dioxide, we are going to heat the world. We're putting in more molecules that absorb the IR energy, okay? And even methane does it as well. Methane by itself, head up, straight 1-to-1, is about 80 times stronger IR absorber than carbon dioxide. That's scary, but methane gets oxidized by the oxygen and converted to carbon dioxide in about 10 to 20 years. And so that reduces its ability, they say around 20, 25 times stronger. But there's only 2 parts per million. So we wouldn't want this to be real high because it's so much more powerful. And the problem is we have reserves out there that are frozen that could be released, and then that would be a tragedy because we'd be taking this 415, which is already bad, and just blowing it up into a huge number. So now if we look at the amount of carbon dioxide per all the molecules, it's only 1 out of about 2,400 molecules. You say, oh, well, that's nothing. How can that do anything? And if we look at the water, say it's at 2,000 parts per million, that's about 1 out of 500. That also looks like nothing. Looks like, what can you do? And then we look at the methane, 2 out of 1,000,000, that's 1 out of 500,000. And again, it's just, you just think this is meaningless. It's so tiny. So is it really possible that such small amounts can have such a profound influence on our world? Let's take a look. Okay, so remember what's happening. That water molecule, or that carbon dioxide molecule, is bouncing all over the Earth, but some of it's at the surface where we're giving off this IR energy. And so the IR energy can be transferred to the water and the carbon dioxide, and then it's up into excited state. And then that water or carbon dioxide can bounce into other molecules, of which we have about 99% of the other stuff, and transfer its energy and make them increase their kinetic energy, their energy of motion. But then they relax back down. But what are we doing? We're constantly shining in more sunshine. And it's excited and relaxed and excited and relaxed and excited and relaxed. So we can transfer and dissipate that energy throughout the entire atmosphere. And that's going to increase the temperature. This is the greenhouse effect, what we're talking about. Remember that microwave. Microwave, even smaller energy than this. But if you keep bombarding those water molecules, they keep pounding on the food molecules, and they keep increasing the temperature again and again. That's your 5-minute climate change experiment. Okay, we're doing this on a much slower scale to the Earth. So let me use another analogy here. I like to play pool, maybe you do too. But when you play pool, there's only one ball that you actually hit. That's the cue ball. So you have this pool stick out here, and you got your cue ball. And then you got all the other balls on the table, a lot more of them. So you got like 15 of these guys out here. And we never actually touch these balls once with that pool stick. Okay, all we ever do is hit the cue ball. So we rack them up, we slam that cue ball into all those balls, they shatter everywhere. That energy that we transfer to this guy is given to all of these other guys. And the effect is profound. You might knock some in on the first hit. And then we keep playing. We keep hitting the cue ball over and over and over. So this pool stick is like the IR photon. We're exciting this, and it's transferring its energy to many other particles out there. And then after a little while, the game's over, and most of the balls are in the holes. And what do? You take them out, you rack them up, and you do it all over again. And you do it all over again. How long can you do that? You can do that as long as you want to play the game of pool. Okay? And that's what we're doing in the Earth's atmosphere. Okay? We're slamming those carbon dioxides and water molecules with IR radiation, and they are slamming their energy into the other molecules out there and increasing the temperature. And we never once touched any of these balls with the pool stick. It's always the photon, the IR photon, that we're transferring to the carbon dioxide and water. Now another thing to think about is, if carbon dioxide is so insignificant, how is it possible that that small amount of carbon dioxide can feed all of the plants and the plankton on Earth? Okay, if you don't think that's a lot, just walk outside and look around you at all the growing plants and stuff. Think about a forest, the Amazon rainforest. Think about the boreal forest up in the northern latitudes. Okay, think about all the plankton that live in 70% of the Earth's surface in the ocean. That they're all fed by the carbon dioxide that's there. So carbon dioxide, even though it's a little bit of stuff, is a really important molecule in a lot of ways, good and bad. Okay, so we have this other problem of looking at carbon dioxide or carbon. So different people look at it different ways. Because not all the carbon in the environment is carbon dioxide, some people prefer to talk about carbon just as carbon. And so they take the carbon dioxide and they look at just the fraction that is carbon. So of the carbon dioxide weighs 44 grams, and 12 of those grams are carbon. So if we figure out that fraction, it comes out to about 0.27 is carbon. So that's the way a lot of people talk about it. But other people talk about it as carbon dioxide equivalents. So if I did have some carbon, I could figure out the carbon dioxide equivalent by multiplying by 44 over 12, just the opposite of what we did here. And so that would be 3.7 times bigger times the carbon. So the chart that I have here shows how all the fossil fuels have changed since 1800. And it's looking at it in terms of carbon. Okay, so this is, now these numbers are really weird. This is a gigaton of carbon. Giga means a billion, 10 to the ninth. We'll get into these numbers a little more. But a gigaton is a huge amount because we need numbers like that to look at the amounts that are out there. Okay, so the history of gigatons of carbon put out by humans is down here. You'll notice we start basically zero. This is about when James Watt made his steam engine. And nothing really happens. Even at 1900, 100 years later, we're hardly changed at all. But then as we get closer and closer to where we are today, you'll notice that all these guys are shooting up. And that's our problem. We have to stop these guys. The black is the total from everything. Coal was the first one. So notice coal starts up, and then around here we get to petroleum. So petroleum is very convenient. Right around here petroleum starts. Petroleum is very convenient because it's liquid, whereas coal is really dirty. We don't really want to use coal, but we'll talk about that in a minute. And so these are shooting up. Petroleum actually passes coal, but comes back down. Coal passed it. Petroleum came back. So both of these guys, we have to shut these down. They're really affecting our world. And this is the total amount. Now, if I wanted to convert this total amount of carbon to carbon dioxide, I'd have to multiply by 3.7. So say I had 10 gigatons of carbon dioxide. I would multiply by 0.27, and I would get 2.7 gigatons of carbon, because I'm only counting the carbon. But say I had 10 gigatons of carbon, which is what we have over here from all the different sources, then I would multiply by 3.7, and that would mean I'd have 37 gigatons of carbon dioxide. So we could go back and forth. I use carbon dioxide, so that's what I'm going to stick with. Okay, now remember, giga is a billion. So this is 37 billion tons of carbon dioxide. That's a mind-boggling amount of carbon dioxide. So is our world in danger? It sure is. Okay, this is warming our world beyond what we can tolerate. Okay, it's not really the world's problem. The world could live with the temperature 1, 2, 3, 4 degrees warmer, but humans cannot live with those conditions. Is our world in danger from too much carbon dioxide? Yes, not just in the atmosphere, but also in the oceans. So look at where we started, and look at where we are now, and we're not stopping. We're still moving. And what we need is the goal of a carbon-free world. So let's look a little bit at the carbon cycle. Just, we want to understand, where is all this stuff going? How is it playing out in our world? So I have up here 1 part per million. Excuse me. Remember, we're at 415 parts per million right now. That's in the atmosphere. So that's about 2.1 gigatons, billion tons of carbon, and that's about 7.82 gigatons of carbon dioxide. Okay, so that's what we're looking at. So I have these down in carbon dioxide equivalents. So in the air, we have about 3,240 billion tons, gigatons of carbon dioxide in the atmosphere. We are adding to that about 18 billion tons to the atmosphere every year. Okay, about 480 billion of that goes into photosynthesis. So plants and plankton, they take that up and make our carbohydrates that we use for food. And we're adding in, from the extra carbon dioxide we add in, about 13 billion more. The plants are helping us out. Okay, so this is really nice of those plants, considering that we're eating them. And then the plants at nighttime, they can't absorb sunlight at night. They have to live. And so they give off a little bit of carbon dioxide. They call that respiration. They give off about 240 billion. But you see, we come out a net increase of using up the carbon dioxide. A lot of the carbon dioxide is stored in the earth in the form of carbon. So we have billions and billions of tons, 9,000, 40,000 locked into the earth. Okay, and then respiration of forms in the earth, life forms in the earth and so forth. There's a little carbon dioxide given off here. We have all this old life form that was lived for hundreds of millions of years that got stored in the earth, which we call coal, oil, and gas. Okay, and we figured out a way to go down into the earth and pull this out. And then what we do is we take that and we burn it for the energy that it gives to us, which has helped us out enormously. And then that makes carbon dioxide, which we put out about 40 billion. Previous page I said 37 billion. About 40 billion tons as from human combustion. Now this also has an ocean cycle over here. They call that the slow carbon cycle. This is the fast, like growing seasons every year, cycle through this. But in the ocean, we can also absorb carbon dioxide. And the organisms there can give off carbon dioxide. So they have their own cycle. Of the carbon dioxide we put into the atmosphere, we're adding about another 9 billion tons into the oceans. Now, this was good because it lowered the amount of increase of temperature, the greenhouse gas. But it was bad because once carbon dioxide gets into the ocean, it turns into carbonic acid, which makes the oceans more acidic. But we'll talk about that a little later. Again, notice these amounts stored in the ocean and deep ocean and earth down here in the sediments. These are huge amounts of carbon. Okay, we would never want to let any of this out because we're working in maybe hundreds up here, altogether maybe 3,000, and we're talking, way more carbon dioxide here. So this is also a cycle where the carbon's going in and out. Some of it helping us and some of it not. I just wanted to make another little picture to emphasize this idea of transfer of energy from the surface of the earth. Okay, this is a little bit redundant, but the visible light comes in, okay, and then it's visible, we see that. But once it hits the earth, it gets absorbed and converted into infrared light. So all over the surface of the earth, we have this infrared coming off. And the molecules of the atmosphere are banging into the surface, and some of them, the water, the carbon dioxide, the methane, can pick up the energy that's here, go into an excited state. And then they transfer that energy by banging into the other atmospheric molecules, the nitrogen, the oxygen, the argon that's out there, and transfer their energy back out. Now, they can do it front and back, left and right, up and down. So some of this energy doesn't just like immediately pop out to outer space. It's bounced around in the Earth's atmosphere over and over and over and over till it works its way back out. Okay, it will ultimately go out. It'll reach an equilibrium where the energy coming in is balanced by the energy going out. If we add more carbon dioxide and water, then the balance will be at a higher temperature level because we have more of these guys in here interacting with the IR at the surface. And so as we put in more, the temperature goes up. As we take out carbon dioxide, the temperature goes down. And so that's sort of, I hope, sort of how that's working. Remember, the predicted temperature of Earth without the greenhouse is 255. We could not live in that world. But with the current comfortable 280 that we had for thousands of years, we had a 288 degrees Kelvin. That was very comfortable 60 degrees. So we are changing this. We are putting in more carbon dioxide, which is raising this temperature up. Very slowly. It takes time to react, but it's raising up. Okay? Now, things that increase the carbon dioxide radically are called feedbacks. So there's things out there that if we keep doing it, we're going to up the level of carbon dioxide, or even worse, up the level of methane, and then we're in big, big trouble. Just remember, there's some reflective parts of the world. There's the ice at the North Pole and the South Pole, and that reflects the light back to space, and so that's a protective thing, that albedo effect. One downside is that we are melting all the ice in the North Pole. So if all the ice melts, we lose that reflective effect, and now we have the blue water, which absorbs the energy much better. And so the absorption of energy will become greater, and the temperature of the Earth will increase. That's one of those tipping points, where if we melt all the ice, then all of a sudden we have this bad effect. So I have another little analogy here. Hopefully they mean something to you. I just seemed like it worked for me. Say you're laying on a bed and your body's radiating out heat. So if it's say a summer night, you might say, I don't need any sheets, I'm perfectly comfortable. But say it starts to get a little cool, it's autumn, gets a little cool, and your heat that you're radiating is being lost to the atmosphere above you, and so you're getting a little chilly. So what do? You go over and get yourself a sheet. So you take that sheet and you put it over the top of you. So now the heat that's radiating off your body is hitting the sheet, bouncing back, it's being bounced around, a little bit leaks out at the edges, but now you have more heat staying in here and you feel a little warmer. But maybe it's a little bit colder than that. So you go and get a blanket. So you put a blanket over you, much more effectively captures the heat that's coming off your body, and so that cycles around and keeps you warm. And so this carbon dioxide that we're putting into the atmosphere, which also increases the water in the atmosphere, is making our Earth warmer. So if we're in an ice age, this is a good thing. We're warming ourselves up. We're putting on extra blankets. But if we're in a warm, comfortable place, we don't want it to go into like a sauna bath. We don't want it to become so hot that we can't live inside of it. And so then we need to reduce the amount of carbon dioxide. So now if you look at how the Earth has played out, we didn't have people here all the time pumping out oil and natural gas and digging out coal. We had just the Earth. How did the Earth increase it? Well, the Earth has always had volcanic activity, sometimes incredible amounts of volcanic activity. Okay? And when the volcano explodes, it puts out carbon dioxide, it puts out methane, it puts out sulfur oxides, it puts out dust particles, all kinds of stuff. The sulfur oxides actually block the sunlight from reaching the surface. They can form sulfuric acid and sulfurous acid. And so for a while, they can make the whole Earth colder, cooler. And so they get into what, say, a volcanic winter for maybe a year, or 2 years, or 3 years, sometimes quite cold. Maybe a little mini ice age could happen. But the thing about the sulfur oxides is they wash out with water. Because we have a lot of water, after 1 or 2 or 3 years, these will all be washed out. But the carbon dioxide that's there will last for hundreds to thousands of years. So all of a sudden, the effect which originally was cooling can turn into be a warming effect from the carbon dioxide and methane blown out. Now what we've done, instead of just one big old volcano that's blown up, it has a significant effect. What we've done is we've sent down millions, over 1 million wells, oil wells. We have natural gas wells, fracking now. We have coal mines all over the world. And we are just pouring out all these fossil reserves, this fossil fuel reserve right here, in a way larger amount than a single volcano over here. They estimate that we're doing it about 100 times faster than a volcanic explosion. And so we're doing it better and better, getting more and more efficient. Okay. In fact, some people are almost afraid we're running out, although we have hundreds of years of coal. So we have to stop this. Okay, this was a good thing for 250 years. This made us what we are today. But right now, we didn't understand that it's also a bad thing, and so we have to somehow convert ourselves from this to alternatives, which we have. So there are choices that we can use. Now remember, all this stuff is the energy from the sun. But it's the energy from the sun that was buried in the earth and converted into coal and oil and natural gas. Okay, so it's like a bank account. It's just your savings account of energy from the sun. The sun just gives its energy every day. Remember, that's like a little checking account. But this is like the savings account. It's just, we've gone crazy. Okay, we're just pulling all our money out at once. And we really can't do that. So I want to look at these cycles one more time because I want to look at the rate of change. So here it is, down and up and down and up and down and up, like we were talking about before, for 400,000 years. So I'm going to come down here to this last little part right here, because we were at an ice age, and then all of a sudden we started heating up to get to the climate sweet spot where we've been. Okay, and just look at how fast did the temperature change there. So I'm just ballparking it. I guess that's about 20,000 years. Okay, was my guess. And it looks like we're going from about -8 Celsius to about 0 Celsius. That's about 8 degrees Celsius change. And so if we figure that out, how many degrees per year, it's really tiny, 0.0004 degrees Celsius per year. Now let's take a look at us and our carbon dioxide. Okay, and so you see carbon dioxide has shot up like crazy. Well, remember there's a lag time. If you put the water on the stove and turn on the fire, it doesn't boil instantly. Okay, it takes some time to make that happen. And so this increase in carbon dioxide is being followed by an increase in temperature. And the increase in temperature for the last 100 years has been about 1 degree. So we've warmed up about 1 degree in 100 years. Okay, so what does that come out to be? That comes out to be about 100th of a degree per year. Sounds pretty tiny, 100th. But let's compare it to the time where we came out of the Ice Age. So we have 100th over 0.0004, and that means we're heating up the Earth about 25 times faster. So estimates I've seen have been from 10 to 100 times faster. Okay, and we're already committed pretty much to another degree. Okay, we have the carbon dioxide in there that hasn't responded, the temperature hasn't responded to that yet. So we're not going to only just go up this 1 degree, at least 1 more degree. That is humongous. We cannot go up 3 degrees, 4 degrees. Okay, the energy, remember, that's the temperature of the Earth. Remember, that was about 5 times 10 to the 14th square meters. All of that is going up 1 degree. Humongous amount of energy. Okay, so fossil fuels control everything. That's the part that's really scary. Until about 300 years ago, human beings were basically subsistence livers. Life depended on the sun's energy. And it's estimated that about 550 gigatons, remember giga is a billion, 10 to the 9th, tons of carbon in life forms. So for 2 to 3 million years, carbon dioxide cycled 180, 280, 180, 280. That's the Milankovitch cycles. And when the temperatures were higher, carbon dioxide was higher, that was better. And when they were lower, we had the Ice Age, which was a very brutal, hard existence. But life, we continued through it. Humans actually lived through an Ice Age before we got to this climate sweet spot. So 250 years ago, James Watt got that steam engine, and it ran on coal and changed everything. Okay, all of a sudden, we could do all kinds of things we could never do before. We didn't have to live off the sun. We had this whole savings account of energy that we could do things. Like we could build trains, and we could make cars and planes, and build buildings and heat them up and cool them down. And it just made the world a lot better place. The first energy we used was coal. Coal was, it's a good energy source, but it's a disaster environmentally. Coal is loaded with heavy metals. It has sulfur in it that becomes sulfur dioxide when we burn it. That turns into sulfuric acid. The heavy metals like mercury. Coal has spread mercury all over the earth. So we have mercury everywhere because we're burning coal everywhere. So that is a problem. So coal, besides putting out carbon dioxide, has these other effects that we don't really want to follow. So what I'm going to do is I'm going to look at 3 forms of the fossil fuels and hydrogen. So the one that now they're touting as methane, they're saying that's the bridge fuel. That's a lot less pollution and not so much carbon, and they tell us stuff like that. But when they take out methane from fracking wells and stuff, they release a lot of methane. And methane is way stronger greenhouse gas. They are not good at all. They have natural blowouts and stuff. They had a blowout in someplace in the United States, I think it was Oklahoma, that blew out as much methane in just a few weeks as all of Europe in a year. So yeah, this is good if we don't leak it out, but we're leaking it out. And there's stores of earth where it's in peat and permafrost and things where there's tremendous amounts of methane. Octane would be sort of like gasoline. In fact, when you go to the pump, they say the octane rating. So I'm just going to pick a simple molecule to be the example of all the fossil fuels that we're going to burn. And then we have coal, and so I picked a pretty famous molecule called benzopyrene that is made when we combust things incompletely. So if you smoke cigarettes, if you like the really kind of black, crusty on your levels of your meat, this has benzopyrenes. And these are not good environmentally. If you eat them inside you, they can turn into carcinogens. But that's not really our point right here. We just want a big molecule that looks something like coal. And then I have hydrogen gas. Notice no carbon on hydrogen gas. Now for all of these, what we're going to do is we're going to combine them with oxygen. And I'm not going to go into an equation about how this all happens. But we're going to take those fossil fuels which have carbon and hydrogen. We're going to mix them with oxygen. And that's going to produce carbon dioxide and water. Now we don't care so much about the water because 70% of the Earth's surface is water, and this will just reach equilibrium with the oceans. But we do care about the carbon dioxides because that's going to last hundreds to thousands of years. The other thing that happens when we do this is we make a lot of heat. Okay, this heat of combustion is energy or heat, so we'll just look at it as heat that comes off. That's the consequence. So I have over here like the methane combined with oxygen, the octane combined with oxygen, the benzopyrene combined with oxygen and hydrogen. And so you'll notice with methane there's only one carbon. I only make one carbon dioxide. Okay, with octane there's 8 carbons. I make 8 carbon dioxides. With benzopyrene there's 20 carbons. I make 20 carbon dioxides. So I drew those molecules out here. Not that you have to understand them exactly, but just look at all the carbons that are in there. And then the hydrogens, they give us energy too. So there's only 4 hydrogens here. There's 18 hydrogens here. Those are all going to make water molecules. But notice the ratio. Okay, the ratio of hydrogen to carbon here is 4 to 1. The ratio here is 18 to 8. That's a lot lower. And notice here, there's actually less hydrogen than there is carbon. This is going to be a bad molecule for burning because it's putting out way more carbon dioxide. Now, if we combust these, it looks like the fuel is like getting better and better. About 800 kilojoules. Remember, that's going to be times 1,000. So that would be 800,000 joules. And then down here we have about 5,000 kilojoules and almost 10,000 kilojoules. So it looks like this is a lot more energy. But remember, it's a huge molecule. It's 20 carbons, and this is only 1 carbon. So it's not really that much more efficient as an energy source. And hydrogen doesn't have any carbon, but we're putting out a lot of energy still. If you look at the percent carbon, this is why they say methane is better, because it's 75% carbon, whereas the octane is 84% carbon, and the benzopyrene is 95% carbon, almost all carbon. And remember, this approximates our coal. So the coal is more dirty in terms of putting out carbon dioxide, but it's also more dirty in terms of putting out heavy metals like mercury and sulfur oxides, which make sulfuric acid. Okay? A lot of disadvantages of coal. And then hydrogen is like this dream energy source if we could only take advantage of it. Okay? So I just want to mention, I have some terms up here, moles and things. A mole is a certain number so that we can compare the same amount, 6 times 10 to the 23rd. Just take that mole and make it a dozen. So if I had a dozen, I'd have 12 of whatever I'm talking about. If I had 2 dozen, I'd have more. If I had 3 dozen, I'd have more, 36, and so forth. Okay, and a molecule, that's just a neutral collection of the atoms, 2 or more atoms. So instead, we're going to sort of calibrate everything to the same level of energy. So we're going to take 1,000 grams. Remember, there's 28 grams per ounce. So if I made that into something more familiar, that would be about 36 ounces. That would be about 2 pounds, 4 ounces. So just to give you a ballpark image about what we're talking about. Okay, so if we take 1,000 grams of methane, okay, it only weighs 16 grams per mole. We'd have 62 moles. Remember, that's kind of like dozen. That's like we have 62 dozen of these guys, except that a mole is 6 times 10 to the 23rd. For oil, if we did it, there's 114 grams per mole, so we'd only have about 9 moles of octane. So that's a 9 dozen. So notice we have a lot more methane in number than we do octane. And if we took the coal, it weighs, the benzopyrene weighs 250 or so. That's about 4 moles of the benzopyrene, about 4 dozen, sort of. Now, if we come down to the hydrogen, they're really tiny. There's only 2 grams. Only 2 grams, so we'd have 500 moles in our 1,000 gram sample. So that's another advantage. Now, how much energy is released if we burn all that 1,000 grams up there? Okay, well, pretty much. Remember, for every mole, we made 794 kilojoules, so that would give us almost 50,000 kilojoules for that 1,000 grams, which was just over 2 pounds. Okay, so we get all this energy that's released. If I took the octane, it releases a lot more per mole, but remember, we have a lot fewer moles. So it actually comes out less energy for the 1,000 grams than the methane. So that's another reason they say methane is good. And then if we look at the benzopyrene, which approximates the coal, we got a lot of energy, but we only have 4 moles, only like 4 dozen. And so there's even less energy, not even 40,000 kilojoules. Now, if we come down and look at the tiniest little guy, the hydrogen, because it's so tiny, even though this small amount that we have here is multiplied by 500, we get almost 120,000 kilojoules. It's double the methane. Okay, So this is a tremendous amount of energy, and it doesn't release any carbon dioxide. Okay. So how much carbon dioxide is released with each 100 grams? Well, the methane had the fewest amount of carbon dioxide, only 2750 grams, because we multiplied by the carbon dioxide divided by the carbon, like we did before. And that comes out to be about 6 pounds of carbon dioxide. Remember from our 2.4 pound, 2 pounds 4 ounces up here. That's because we're adding in oxygen. And then the octane would generate about 6.8 pounds, so a little more carbon dioxide. And then the benzopyrene, approximating coal, would add about almost 8 pounds of carbon dioxide. And then if we look at all those 500 moles of hydrogen, we burn them, the answer is 0. The only thing we make is water, which is perfectly compatible with our world. So this looks like a dream. Okay, hydrogen looks great, but the problem with hydrogen, it's a very, very low boiling gas. So it's a gas in our world about minus 223 degrees Fahrenheit. And it's extremely reactive with oxygen. It wants to make water. And so it's very explosive. Okay, if we were to have a gas tank that had hydrogen, we would need a really highly pressurized gas tank. It'd be under high pressure. It'd be very hard to transfer, say, to a car or a bus or a truck. So it would be tough to work with, and it would be very dangerous. If you had a little bit of a leak at a pump with oxygen in the air, you'd have a tremendous explosion that could happen. If you were in a car accident and the tank were to rupture, it would probably be an explosion. So there's a lot of inconvenient things about hydrogen. So far we haven't figured out how to solve these problems. But they do have hydrogen cars, burning cars. They run them in California. They have hydrogen fueling stations where you can go. They're not all over the place, but there's one in the city close to where I live. And so if you have one of those cars, you're allowed to go over there and fuel up. They have nations like Japan and Germany who are working on this. This is the kind of stuff we need to be doing. We need to be working on developing this stuff as an alternative to what we're doing over here. But we're not. Okay, there's a few people doing it, but we need a huge effort. Okay, just a reminder, whenever they talk about calories of food, that's a kilocalorie. Okay, and so normal person might eat around 2,000 calories. To give you a sense of proportion, if we convert that to joules, that would be about 8,400 kilojoules. And that's 1,000 little joules for each one. And then the amount of grams is about 28 grams per 1 ounce. Okay, so the calculations I'm going to do below are to give you a sense of proportion to what it is that we're doing. Okay, so first off, I'm going to take all the fossil fuel combustion, the coal, the oil, the natural gas, and I'm going to pretend like it's octane, because we know the energy that's released when octane burns. And we're going to use that as an equivalent to calculate the energy for everything that's being burned. Okay, you can just look at roads like this. Every time I drive down the freeway in a traffic jam, I'm just looking at all of that fossil fuel burn. Next, we're going to take a humongous amount of energy, a Hiroshima-sized atomic bomb. We're going to compare that energy released in that atomic bomb to all of the energy released when we burn the fossil fuels in 1 year. Okay? Now, we know this is a tremendous amount of energy. Okay? It obliterated entire cities, 2 of them, Hiroshima and Nagasaki, and back in August of 1945 at the end of World War II. Over 200,000 people were killed in an instant, in a second. So the thing about this energy that's released, it's not released over a year. It's released in less than a second. Tremendous amount of energy, extremely intense. Okay? So you would think after we saw something like this, over 200,000 people annihilated in a second, and entire cities leveled to nothing, that we would never ever come back to this again. But instead, it's estimated we now have 9 or 10 countries of the world. We have over 14,000 nuclear weapons. So this is a problem as well as climate change. So far, we just haven't blown them up, so we hope we never do that. So what we're going to do is we're going to compare these 2 energies, the energy of combustion in a year and the energy of a Hiroshima-sized atomic bomb. And we'll compare these in time, and we'll compare these in area of the Earth. Okay? And then the final thing we'll do is we'll estimate all of the energy released in climate change and heating the Earth 1 degree. And we'll compare that to the energies above as well. And we'll see how these things actually compare. Do we really have to be worried about climate change, the energy down here, compared to all the fossil fuel combustion in a year, do we really have to worry about that? We'll get some numbers and we'll tell you what it looks like, okay? Ballpark estimates. But we'll do it degree by degree. We'll do it at 1 degree, 2 degrees, 3 degrees, all the way up to 8 degrees to show how that energy affects our world. So let's look at first the fossil fuel that humanity burns in a year. Okay, so I said before we put out about 40 gigatons, say last year about 40 gigatons of carbon dioxide. Giga is a billion, that's 10 to the 9th. Okay, so we're going to want to convert that to something we can convert to moles. So we're going to have to convert that to grams. Okay, now remember only 0.27 of that carbon dioxide is carbon. So that's 12 grams of carbon out of the 44 grams of carbon dioxide. So if we wanted the grams of carbon, we'd multiply 0.27 times 40, and that would give us 10.8 gigatons of carbon. Okay, or we can just use the mass of carbon dioxide. So this is the equation, and you can see that one molecule of 1 mole of octane or molecule will make 8 molecules or 8 moles of carbon dioxide. We need this conversion because we're using octane as our reference point. So this is going to be the carbon dioxide that comes off of that. Okay, and then this water and carbon dioxide and heat is going to spread all over the earth. Now the mass of carbon dioxide, how do we do that? We need the molecular weight. So we have our 40 gigatons, that's 40 times 10 to the 10th tons of carbon dioxide. And we're going to say a ton is 2,000 pounds. We won't go with the metric ton, we'll just say 2,000 pounds per ton. But we need grams, so then we need a conversion, 454 grams per 1 pound. And when we multiply these out, we come out with the grams of carbon dioxide. Okay, so that's just the weight of the carbon dioxide. Huge number, 3.6 times 10 to the 16th. But what we need are moles. Okay, remember, moles are the number, so like a dozen. And so I have these grams, and then I use the molecular weight. 1 mole takes up 44 grams. And so I'm going to multiply that out, and I get 8 times 10 to the 14th moles of carbon dioxide. So the reason I want moles is because I know the energy released for every single mole. And then I can multiply this by the energy per mole, and then that will tell me how much energy we're releasing. But first I have to figure out the moles of octane. So the moles of carbon dioxide I have to reduce by 1/8, because there's only 1 mole of carbon in the carbon dioxide, and there's 8 moles of carbon in the methane. In the octane. And so that comes out to be 1 times 10 to the 14th moles of octane from our 8 times 10 to the 14th moles of carbon dioxide. 1/8 is what we're looking at. Now I know the energy that's released when a mole of octane is burned. I told you that before was 5 times 10 to the 3rd kilojoules per mole. We have 10 to the 14th moles. So we multiply these out, it comes out to a really big number of 5 times 10 to the 17th kilojoules of energy. Remember, a joule is a little amount of energy that we use to heat up that one little cube of sugar in the form of water. Okay, and that's released per year. Okay, that's per year. So our 4.0 times 10 to the 10 tons of carbon dioxide produces this many kilojoules, but we're going to work in joules, so we have to multiply 1,000 times this, because there's 1,000 joules per kilojoule. So now we have 5 times 10 to the 20 joules. Again, these numbers are so big that we can't even comprehend what they are. But it's just a tremendous amount of energy, as we'll see in just a minute. Okay, so now let's calculate the amount of energy released when TNT, when a atomic bomb explodes, which is 12,000 tons of TNT for the Hiroshima-sized atomic bomb. 1 ton of TNT has 4.2 gigajoules. Remember, that's 10 to the 9th joules. And so we can write it in this form here. All right. Remember, kilo is 1,000. So I have 1 Hiroshima bomb is 1.2 times 10 to the 4th tons of TNT times 4.2 times 10 to the 9th joules per ton. And that tells me how many joules I released when we blew up that Hiroshima-sized atomic bomb. 5 times 10 to the 13th. Okay, in 12,000 tons, or 12 kilotons of TNT. Now what we're going to do is we're going to take all the energy that we release in combustion in a year in joules,
And we're going to divide it by all the energy released by a Hiroshima-sized atomic bomb. And when we do that, we got 10 to the 20th over 10 to the 13th. We come out with 10 to the 7th. That's 10 million Hiroshima bombs going off per year to equal the energy that we release when we combust all the fossil fuels. Okay, so how much is that? If we calculate the number of seconds in a year, okay, years, days, hours, seconds per hour, we come up with about 30 million seconds per year. So what we're going to do is we're going to divide the number of Hiroshima bombs, which is about 10 million, by the number of seconds, which is about 30 million. And that's going to come out to about one Hiroshima bomb every 3 seconds. Okay? That means every 3 seconds, an atomic bomb size amount of energy is being released into the Earth's atmosphere from the combustion of the fossil fuels. That's mind-boggling. Okay? That's a humongous amount of energy. Now, I will point out one thing. The Hiroshima atomic bomb released all of its energy in a second. So that's a tremendous amount of energy in a very, very short time period. And it was all concentrated at the point of explosion. Whereas the Earth, we have a tremendous amount of energy, as we just saw. It's the equivalent of 30 million of 30 million of those, 10 million Hiroshima-sized bombs, one every 3 seconds. But that's spread out over the whole surface of the Earth and the whole course of a year. So the energy content, the energy density, is a lot lower than blowing up atomic bombs everywhere. If we look at how much of the land is covered by those explosions, we could do another little experiment here, thought experiment. The surface of the Earth is 4 pi r squared. The radius is about 4,000 miles. And so we multiply that out. So the surface of the Earth is 2 times 10 to the 8th square miles. But we're only looking at land, so we take 0.3 of that, because the oceans are about 70%. And so that gives us about 60 million square miles. Is that right? 60 million square miles. And up from above, we had one Hiroshima bomb. We had 10 million Hiroshima bombs. So that would correspond to one Hiroshima bomb for every 6 square miles. That's a lot of bombs. It covers a lot of the Earth. Now, it turns out that if you had a plot of land that's 2.2 on a square, that would be 6 square miles. It's said that the Hiroshima atomic bomb destroys everything within a 1.4 mile radius. If we figure out the area of a circle with a radius of 1.4, it comes out 6 square miles. So that means we have enough Hiroshima bombs up here to cover every square inch of the land on Earth with an atomic bomb explosion. But again, the intensity is very different. It's not a second, it's spread out over the entire year. But still pretty incredible. The amount of fossil fuels we are burning and the energy we are making from burning those fossil fuels per year is humongous. Okay, so now we're going to do a third calculation that's going to allow us to see how does climate change compare to this. Okay, so this is a little more challenging, and we have to make some assumptions, and some people might disagree with the assumptions, but they're just ballpark figures. So that'll give you an idea of what it is we're doing, because otherwise they just tell you we're putting out a lot of energy you don't really know. Now, in reality, the people who really do this, the scientists, are much more sophisticated than I am. They have elaborate computer models that consider all kinds of factors that are just minute details and a lot of things they're tracking. I'm just taking one equation, one calculation, and looking at the energy that's predicted from it. And it's going to be in the ballpark, okay? It might not be as good as the really sophisticated scientists doing the computer calculation, but it's going to tell us something, okay? So I'm going to go back to the Stefan Boltzman Law. Remember, we had this simple little constant, very tiny, 5.7 times 10 to the minus 8, times temperature to the 4th, okay? So the temperature to the 4th really impacts this equation right here, okay? And we're going to come out with energy in watts per square meter. Okay, and then we can figure out how many square meters are on Earth. We already did it. We'll do it again. Okay, and so then what we're going to do is we're going to change the temperature in the Boltzmann equation from our starting temperature by 1 degree. And then we're going to change it by 2 degrees and 3 degrees, all the way up to 8 degrees. Okay, 8 degrees would be the worst possible case scenario. I mean, if we go up to 8 degrees, humanity is done. There will be no humanity as we know it. So this is something we cannot do. Now, it's very unlikely we're going to do that, but it is possible we could hit 3 or 4 degrees if we do not change anything within 100 or 200 years. Okay, so let's take a look. I'm only going to do the calculation for the starting point and the first degree. I'll just write the data for the rest. You can check me if you want to repeat those calculations. So first, let's calculate the energy generated by Earth as a black body based on its 288 degree temperature. We already did that. We did it way early, a long time ago. So if the temperature is 288, I'm going to put that in here. Okay, I'm going to take it to the fourth, multiply the Stefan Boltzman constant times that. So I come out with 392 watts per square meter of surface of the Earth. Okay, so remember, watt is a joule per second for every square meter of the surface of the Earth. And I think that was around 5 times 10 to the 14th square meters. Okay, so that's our starting point. Now, what if we increase the temperature 1 degree? Sounds like nothing, really. Okay, so I'm going to go through and do the same calculation, but this time I'm going to use 289. So just a little 1 degree increase. We've already done that. The Earth is 1 degree warmer already. Okay, actually, we put so much carbon dioxide in, they say there's no chance that we can stay under 2. So we're probably going to hit 2. Our only chance if we start working like crazy is that we might be able to keep it under 3, but we're not really working like crazy. We're not really doing anything, just about. And so it's very possible we could hit 3. But let's just take a look at this 1 degree extra. So now the total energy at all the wavelengths at 289, instead of 288, I'm going to put 289 here, raise it to the 4th power. That's the big clue there. And so that's going to give us 398 watts. Remember, that's a joule per second per square meter. Okay, so here we have our two energies. Energy at 288, energy at 289. What does that translate into? Okay, well, I need the area of the Earth because I need all the square meters. I already did that before, but I did it again here for you. And I also need all the time of a year. We already did that before, so I did that here again, just so you can see it. And now let's take a look at the energy that we're comparing. So the energy, I'm taking the Stefan Boltzman equation. I'm calculating the energy at 288. Okay, so that's going to come out to be, I have this many square meters. I have this many seconds, and so I come out with this much energy for the Earth for a year, for a whole year. 6.52 times 10 to the 24th joules. That's a mind-boggling amount of energy. But then I do the same thing for the 1 degree warmer, and so my starting point here is 398 joules per second per square meter. Remember, we reported this as watts. And now the amount of square meters is the same, and the amount of time is the same. And I get 6.62 times 10 to the 24 joules. Again, a humongous amount of energy. And when we look at these two, they look like they're not very different, 6.62 and 6.52. But let's take the subtraction and see. So then I come down here and I take the difference of those energies. And sure, 6.62 minus 6.52 is only 0.1. But what we forgot is we're multiplying it by 10 to the 24. So let's go ahead and use up one of those 10s and make it into a 1. So now we have 1 times 10 to the 23 joules. This is the energy that came about from a 1 degree increase in the entire Earth surface, entire Earth environment. Okay? Now remember, we have some other energies we can compare that to. So what we're going to do is first we're going to compare that energy to the amount that released in the atmosphere. Okay? So the amount that released in the atmosphere was about the amount that released in the atmosphere from climate change was 1.0 times 10 to the 23rd. And the amount that we released from all the fossil fuel combusting in 1 year is 5 times 10 to the 20th. So we divide these two, and the amount that's coming from climate change is 200 times bigger than the amount from all of the fossil fuel combusted in 1 year. Okay, 200 times bigger for 1 degree. Remember, this is going into the entire Earth. That's why it's such a humongous number. Okay? Now remember, the amount of combustion in 1 year released the energy of an atomic bomb every 3 seconds. We're doing it 200 times more than that. That means that instead of every 3 seconds blowing up an atomic bomb, we're blowing up 62 atomic bombs per second. Think about the energy that's involved there. This is the amount of energy we are releasing into the Earth's environment from 1 degree increase. Okay, we cannot even comprehend that amount of energy. It is humongous. Okay, now that carbon dioxide stays there year after year for hundreds of years to thousands of years. We're going to keep repeating this experiment over and over from that extra carbon dioxide, from that extra energy. Okay, so now let's come down here and take a look at some other energies. So here's our starting point. Here's our 1 degree that we heated up. Okay, so we released this amount of energy, and that came out with a 200-to-1 ratio with the amount from the combustion in 1 year. What if we heated it up 2 degrees? Then we would have 1.9 times 10 to the 23rd, and we would divide out, that would be 370 times more than the combustion of all the fossil fuel in a year. 3 degrees would be 580. 4 degrees would be 740 times. 5 degrees would be 940 times. 6 degrees would be 1,140 times. 7 degrees would be 1,300 times. And 8 degrees would be almost 1,600 times more energy than all the energy released in the fossil fuel combustion in 1 year. We cannot get to these levels. Okay, the original goal was to not even do this, but then they said, okay, maybe we can handle 1 degree. Now we're saying maybe we can handle 2 degrees. Please don't go to 3 degrees, but probably we're going to see 3 degrees. We don't want to go above that. You can see what happens. Okay, so remember, 200-to-1 ratio translates into 62 Hiroshima atomic bombs per second. So let's take a look at what this energy can do. One of the main things that we're concerned about is melting all the ice. And most of the ice is in Greenland, about 15%, and Antarctica, about 85%. There's a little bit around the world, it's less than 1%, so you think that's not significant. But these glaciers around the world actually supply the water for many, many countries of the world. And if we take away that water, we got a big problem. Think of the Himalayas. They supply Pakistan, they supply India, they supply China. Okay, without that water, we would have some major problems. So that little 1% is, less than 1% is still important, but we're just going to look at Greenland and Antarctica for sample calculations. So Greenland, I've just made it like this oval right here, and then there's a big ice cube on top of it. And I'm going to assume the ice cube is about an area of 670,000 square miles. And then the glaciers are about 0.9, they say, tall. So I'm going to multiply height times area, and that'll give me a volume of the ice. Okay, so that comes out to be about 600,000 cubic miles. Okay, cubic miles. That's a mile, it's a ton, and we have 600,000 of these cubic miles. That's a lot of ice. If we go down to Antarctica, it's a lot more ice. So again, I've kind of simplified everything. I made Antarctica into a giant circle. There's a little blip off to the side here. They call that the Antarctic Peninsula. We're just kind of ignore that because it's like less than 1%. But Antarctica is divided up into 2 different regions, the West Antarctica and the East Antarctica, which has much more of the ice. The West is the one they're concerned with right now because that appears to be melting a little bit faster than it was. So if we look at all the glacial ice down there, that's about 6 million cubic miles. So again, these numbers are so hard for us to comprehend. So we're just looking at big numbers. Okay, so here's Greenland. Here's its ice. And what we want to do is see how much, if all this ice melts, how much will the sea level go up? Well, sea level is the oceans of the world. That's about 70% of the Earth. So we're going to look at the volume of the ice, this many cubic miles, and then we're going to figure out how does that translate into volume of water around the Earth. So we figure out the area of the Earth, and that's 4 pi r squared. We already did it before, but did it again here. That's 200 million square miles. Okay, now the water that melts here is going to raise the level of the sea, so that's going to be our height. We want to get the height that comes out of this volume of water that melts. So the volume of water is this much times the area. Well, we figured out the area is actually 0.7 times this. It seems like I left that out. So 0.7 times this because 70% of the Earth is water. So that's going to be 141 million. And the volume is this. And what we don't know is the height. with this volume spread over this area, how high is it going to go up? So it's pretty easy. We just solve for h. Right? We get the 600,000 cubic miles over the 141 million square miles, and we get 0.0042 miles. Looks like a kind of a small number, but remember, every mile is 5,280 feet. So if we multiply that out, we get something around 22 feet higher sea level. And the estimates are, I've seen like 20 to 24, some that place in that range right there. So if all that ice melted, that would raise sea level 22 feet. Well, you can imagine what that's going to do to every coastal area. What's that going to do to the rice-producing deltas like the Mekong Delta in Asia? What's that going to do to water tables, say like in Florida, when the salt water comes in and corrupts all the water tables? This is a lot of sea level rise. Okay. Now, again, if you put an ice cube tray into the freezer, the ice doesn't just instantly appear. If you take the ice cube tray out of the freezer, the ice doesn't instantly melt. It takes time. Okay. So I did first let's look at Antarctica. So let's take a look at Antarctica. Antarctica is huge. I had no idea how big Antarctica is. It's a whole continent. Okay. So they say it's has mountains that go up about 10,000 feet. It's about 800 miles across. And it's estimated that there's 27 billion tons of ice in Antarctica. Who even knows what that is? It's just the biggest ice cube you ever saw in your life. Okay, and so big that it pushes the crust of the Earth down about 3,300 feet. If you had a super tanker that carries, like goods from China to America, 335 meters long, 43 meters wide, one ship could sail every second for 860 years before you used up all that ice. Okay. So last year, 2018, they estimate that 200 billion tons of ice were lost, melted out. But really, that's almost nothing. Look at 200 billion up here. That would be just this part right here. So that's just a tiny little bit of the ice. So small compared to the total. They're not too worried about East Antarctica right now, but in the long term, they can be. Let's take a look. So it turns out that Antarctica has this current that goes around that protects it. It's called the Antarctic Circumpolar Current, ACC. It flows around in a clockwise direction. And what that does is it blocks the other currents that are warmer water from coming in and touching this and melting it faster. So it keeps it really cold. That's a good thing, because that means that it's harder to melt that ice down. So we're going to do just like we did before. We're going to assume that all of this volume of ice, which is about 6 million cubic miles, goes and spread out over the area. And now what would the height be? So again, we have the height that the water goes up, sea level rise, times the water area of the Earth, times the total cubic miles in Antarctica, and we get sea level rise of 0.045. Again, it sounds like a small number, but we multiply by 5,280 feet per mile, and we get 240 feet. Well, if this was all to melt, it would be a totally different world. Because remember, Greenland would have already melted, so we'd be up at 260. They think sea level rise is going up actually many hundreds of feet, even beyond this. So that's just our rough calculation. Okay. Now, actually, Antarctic lost about 45 cubic miles, they estimate. And so if I divided that into the 6 million up here, that means it would take about 11,000 years for all that ice to melt down there, the West Antarctic. But the thing that's going against that, it sounds like forever, but the temperature has increased 2.4 degrees Celsius, 4.3 degrees Fahrenheit since 1958. This is the blink of an eye, geologically. And we're still going up. Okay, and we're going up fastest at the poles in terms of temperature. So this 11,000 years is like the longest possible. Probably it could be way faster than that. Now, variations of wind, ocean currents, okay, there's so much uncertainty in this. So we could be like really alarmist and say, oh, it's going to melt and instantly, or we could say, oh, it's going to take forever. We don't have to worry about anything. but really it's someplace in between. Okay. So let's take a look. Oh, I did a little experiment. Ice on land melts really slowly. Okay, ice in the water melts really fast. They tell you that. But what I did was I went to my freezer. I got out 2 ice cubes. Okay, so I got out an ice cube dry, put it in a dry bowl, let it sit there. And then I got an ice cube and I put it in a bowl that was half full of water. And then I started my stopwatch. So what happened was the ice cube in the water was melted in 7 minutes. Okay, so that would be like the iceberg that's out in the ocean. But the ice cube in the dry bowl was still, you can see it's still an ice cube pretty much. So actually, it took me a long time. I kept coming out and checking on it. And finally, at 1 hour and 46 minutes, the ice cube had finally melted. But if you look at the difference here, ice that hits the water, that's gone. Okay, that's going to melt fast. Ice that stays on land, that's going to melt slow. And so right now, we have a lot of the glaciers, like the Antarctic and even in Greenland, that's on land. It's melting slowly. But there's little fissures inside where the water is, there's cracks, and the water is filtering down through it, and it's melting the ice faster. And at the bottom, there's water that's forming at the bottom, making the friction a lot less, and allowing some of those glaciers to slip off a little faster. And remember, as soon as they hit the water, it's going to be gone. So you can do that experiment yourself. Okay, so as a final calculation, I want to look at an approximate time it's going to take to melt all that ice in Greenland and Antarctica. Okay, I'll show you my calculations, check them, see if I did it right. Right now we're saying, oh, it's going to be 11,000 years. Let's see. So the problem with melting ice is we have to add heat. Now there's 2 places we have to add. We have to add heat to the ice, and then when ice gets to the melting point, we have to melt the ice. That's additional heat. So the heat to warm up the ice is called the heat capacity of the ice, just like we did for the water. We had a heat capacity for the water, we called it 1 calorie, and then we made it 4.2 joules. But for ice, it's a little lower. To heat up ice 1 degree, we need to add in 2.1 joules per degree Celsius per gram. Okay, we need these because we're going to figure out how many grams we got there. Now, once we get to the melting point, all of a sudden it takes way more energy because we're not just melting it, we're breaking down the entire structure, the lattice structure of the ice and making it into water. And that requires 334 joules per gram. Okay, remember grams, just 1/28 of an ounce. That's a tiny amount. So now we're going to need some amounts. So for all the ice in Greenland, I have here, 637 cubic miles. We need to convert that to grams. So I converted miles to meters, 1,600 meters per mile raised to the 3rd power. And then I converted meters to centimeters, because I can convert that to grams, raised to the 3rd power. And then I have 1 gram per cubic centimeter. So I multiply all those out, and this huge amount of miles of ice has become now 2.6 times 10 to the 21 grams of ice in Greenland. So the reason I want grams is because that's what I have up here in my units of energy. All right. So now our thought experiment is going to be, we're going to have ice at 1 degree below 0, because we only want to do this 1 degree, just to see what the amount is. And then we're going to heat it up to the freezing point, which is 0 degrees Celsius, and then we're going to melt it. And how much energy is that going to take? So the energy to warm all of the ice in Greenland 1 degree is the amount of grams we have times 2.1 joules per degree per gram, okay, times 1 degree, comes out about 5 times 10 to the 21 joules. That's a lot of energy, because that's a lot of ice. Now, let's see how much it takes to melt all that ice. So to melt all that ice, we have the same amount of grams, but now we have to multiply it by 334 joules for every single gram of the ice. That comes out to 8.7 times 10 to the 23rd joules. So I want to compare these two. So what I did was I took 100 out of here times 8.7 and made it 870. So they're both 10 to the 21. So now I can compare 870 to 5, okay, and I can see that that's very, very tiny. So in fact, what we're going to do is we're going to ignore the energy to warm the ice. It's a lot, but it's not a lot compared to the energy to melt the ice. So we're just going to use this energy here for our comparison point. So this sounds like a lot of energy, but remember, the energy from increasing the temperature of Earth 1 degree was 1 times 10 to the 23rd. If we look up here, this is about 9 times 10 to the 23rd, 8.7 times 10 to the 23rd. Man, we are in the same ballpark. Okay, we're in the same amount of energy. This is 1 year of energy, and this melts all the ice in Greenland. So let's take a look. Here's the extra energy to Earth divided by the energy necessary to melt Greenland ice. And so basically the 10 to the 23rd disappears, and we get 1 divided by 8.7. So that means if we took this energy and we did it year after year after year for 8.7 years, 8.7 years, we could melt all of the ice in Greenland. That is profound. That's just with 1 degree if we put it all into that. But that's not very realistic. Let's say we only put in 1/10 of the energy from the climate change increase of 1 degree. Then that 8.7 would be 87 years. Okay, that's a little more reassuring, but that's still, this century, all the ice in Greenland would melt. So let's just say it's 1/100th of the energy goes into melting the ice. Then that would take 870 years, and we might be saying, oh, okay, I'm breathing a sigh of relief. 870 gives us a little time to respond to what's going on here. But remember, that was for 1 degree. We are already committed to 2 degrees. Okay, it's going to go up at least 2. We're hoping it doesn't go 3, but it looks like that's where we're heading. And for sure we don't want it to be 4. Okay, because everything that happens here is doubling, tripling, quadrupling the energy, and it's making everything happen faster. So we get some pretty shocking results. So remember, when all that Greenland ice melts, sea level is going to go up 20 to 24 feet, and there's serious consequences to that. So what I did was I repeated the temperature increases, 1 degree, 2 degree, all the way up to 8 degrees. Okay, I looked at all the extra energy from the Stefan Boltzman Law. Okay, it's doubled, it's tripled, it's quadrupled approximately. And so what that does is that cuts the time factor down, the ratio. So here it was 1 to 8.7, but if we double the energy, then it's 1 to 4.6. If we triple the energy, it's 1 to 3, and so forth. And so if we took all of this energy and used it to melt the Greenland ice, say we went up 3 degrees, we could melt all of Greenland with 3-degree increase in climate change in 3 years. Now, we're not thinking it's all going to go to Greenland. We got Antarctica, we got the whole rest of the world. So if we said it was 1/10, that would be 30 years. If we said it was 1/100th, that would be 300 years. Okay, so that's a lot longer, but geologically, that's a blink of an eye. Say it was 1,000, that would be 3,000 years. Geologically, historically, this is the way the world worked in thousands of years. 3,000, 5,000, 10,000, 50,000, went back and forth. But remember, there were no people around then. Okay, now we have people over every part of the world. There's no part of the world that doesn't have people, maybe except Antarctica, and even there's a few people there. So we cannot have changes like this in our world. When there's just Earth everywhere, it doesn't make any difference. It's just Earth. It responds. If perhaps we were able to go up to 8 degrees, it would be a nightmare. That means we would put the amount of energy into the world from climate change that could melt all the Greenland ice in 1 minute. That would be like we took our ice cube and put it in a hot pan. It would just melt away in nothing. But at this level, say it was only 1/100th, it would still be 100 years. That would only be 100 years to melt the ice of Greenland. Okay? So that's not real encouraging. Let's take a look at Antarctica. So now we're going to look at the time it would take to melt all the ice in Antarctica. Okay, everything's the same, specific heat, 2 joules per degree per gram. Ice heat of fusion is still 334. But what's changed now is the amount of ice. Now we have 6 million cubic miles. So we convert that to meters, we convert that to centimeters, we convert that to grams, and we come out with 2.4 times 10 to the 22 grams of ice in Antarctica. A lot of ice. Biggest ice cube you ever saw. So just as with the Greenland experiment, we're going to, thought experiment is going to be to raise the temperature 1 degree from -1 to 0. And then we're going to look at the energy to melt. So to raise it from -1 to 0, we take all of those grams and we multiply it by 2.1 joules times degrees per gram times 1 degree. So we get this very large amount of energy. Then we figured out how much it takes to melt, and you'll notice now it's 334 joules per gram. So just as before, the amount of energy is way, way more. So I made the exponents the same, 10 to the 22. So I'm comparing 800 of this to 5 of this. And so just as before, we're going to ignore the energy to warm at 1 degree. We're just going to look at the energy to melt it. So the energy from that extra 1 degree increase turns out to be, the energy from climate change, 1 degree, is 1 times 10 to the 23rd, which we've already shown before. But the energy to melt all the ice is 2.4 times 10 to the 22. This is 10 to the 23. So you see we're quite a bit bigger than we were before. But the energy has to be multiplied by 334. So that comes out 8 times 10 to the 24 compared to 10 to the 23. Okay, so this is about 80 times bigger for all the energy to melt Antarctic ice. Okay, so this was 8.7 for Greenland. Looks like I should, that was for Greenland. The energy to melt all the Antarctic ice would be 80, it would take us 80 years. Okay, because Antarctica has a lot of ice. If we did 1/10 that energy, it would be 800 years. If we did 1/100th of that energy, it would take us 8,000 years. That's starting to look more like what would typically be the case historically. But that's just 1 degree. So remember, we're pretty much committed to 2 degrees. Hopefully not 3, but looking like we're going to see 3. And certainly not 4. We don't want that. Okay. So just as before, I looked at all the increases in temperature, the energy that comes from those increases, from adding that energy to the entire world. And now we're going to compare that to the ice, the energy to melt the ice in Greenland. So if we put all the energy into to melting the ice, okay, the ice requires 80 times more energy. It would take us 80 years. If we take 1/10 of that, that would be 800. 1/100th of that, that would be 8,000. And if it was 1,000 of that energy, it would be 80,000 years. So geologically, it's been more like this. But remember, we're putting in heat way faster than historically has occurred. Our calculations was around 25 times faster, and estimates I've seen are 10 to 100 times faster. Okay, but if we went up 2 degrees, only 42 years, or 420, or 4,200. If we went up 8 degrees, the worst possible case scenario, actually 8 degrees could melt all that Antarctic ice in 10 years. But we don't expect it's all going to go there. So if it's 1/10, it would take us 100 years. Still incredibly fast to melt the biggest ice cube in creation. And if we did 100th, that would take us 1,000 years. So we would actually feel the effects of that even immediately if this starts to happen. We're not thinking we're going to hit 8. 4 is a catastrophe. We don't even want to talk beyond that. But there is talk of 5 or 6. Okay? Now, if all that ice melted, remember, at least 240-foot sea level rise, which would change the surface of the Earth. Now, my calculations have a lot of uncertainty up here, and I can show that with the 1/10, the 100th, the 1,000th. I do that on purpose. But even though there's uncertainties here, you got to remember what we're betting here. We are wagering the Earth. And our little bet that we're making in Las Vegas is red or black. We get 1 bet. Okay? And if we're wrong, then that's a big, big consequence. So what I have here is what the computer models predict, just to show you some probabilities. So they have something called the IPCC, the Intergovernmental Panel on Climate Change, and they come out with predictions and status about every 4 or 5 years, excuse me, that tell us where we have been and where we're going. And so they have these 4 kind of predictions that they look at. One is like, it's everything works perfectly. We're going to reach our goals. We're going to cut the carbon dioxide, and then what's going to happen to the increase in temperature? Okay, so they have that little chart over here. I've translated this chart down to this part right here. So they're looking at 1 to 1.5 degree increase, okay, 1.5 to 2 degree increase, 2 to 3, 3 to 4, over 4 degrees. We don't want to talk about this. Okay, so in their little predictions from their computer models, and you can see all these little lines. These are like all the computer's predictions. So you can compare my rough calculation to what these guys are doing. These guys are way more sophisticated. But the ideal case is we would limit the carbon dioxide and actually start to reduce it. Okay, so here's the global carbon dioxide emissions from energy, okay, and industry in gigatons per year. So here's where we were, about 40 last year. Okay, that's where we are right about now. And this is projecting out into the future what's going to happen. So if we're doing everything just right, because we're taking all the carbon dioxide out, we're not burning more fossil fuels, okay, that was their goal at Paris. So I call this the pretend Paris goal. We're not going to do this. But if we could do it, even this doesn't predict we're going to stay under 1.5. Okay, so it predicts there's a 35% chance we could go up to 2. 45% chance we could go up 2 to 3. And then it falls off. There's basically no chance we're going to go over 4 if we can do that. That's good. Tiny chance we could go up to 3. We don't want that either. And so this would be, say, our ambitious effort. That means we're trying, but not very hard. Okay, so we're trying now, but not very hard. We're developing wind and solar. People are developing electric cars. Okay, people are thinking about it. They're trying, but the level is so low compared to the amount of fossil fuels we're burning. Remember, 40 is the highest we ever put out. We're supposed to be lowering down, and the biggest year we ever had was last year. Okay, so this is, we're trying. But if this is the case, where we're not even trying very hard, the highest one is 55%. The best probability is we're going to go up about almost to 3 degrees. There's even a 1% chance we could go over 4. But 1% is not very much. So maybe we make sort of some goals, some effort. Well, look at the United States just pulled out. So how good an effort is that? We're the second biggest emitter in the world, on the Earth. So some effort. And if that's the case, there's a 52% chance we're going to hit 3. There's a 34% chance we're going to hit 4. And there's a 7% chance we're going to go over 4. Now, if you're getting on a plane and they said there's a 7% chance that plane's going to crash, you probably wouldn't get on that plane. Okay, so even though that's a low percent compared to these. And just to tell you, 3%, think about that Greenland ice. Okay, that Greenland ice is going to go fast. A lot of consequences. Say we made a feeble effort. Really, that's kind of like what we're doing right now. With the United States not even involved or engaged, you can't even call that some effort. It's a feeble effort. And if we look at the projections out here, biggest projection is 3 to 4 degrees. We even have a 1 out of 3 chance we're going to go over 4. If we go over 4, even the Antarctic ice is going to start to go. And there's a lot of consequences I'm not talking about, because I'm just trying to show you the effect of this energy in the Earth. Okay, if we make no effort at all, then the number one possibility is we're going to go over 4%. Okay, that's what the computer models predict. And the computer models have been very good, very close in terms of their prediction. In fact, they're a little under the prediction of the bad things. They're actually a little better, most of them. Now, there's one thing I have to switch to and talk about. This is called global warming's evil twin. This is ocean acidification. Now, at first, we thought this was a good thing. It turns out that all the carbon dioxide we put in, a big chunk of it goes into the ocean. That means it's not in the atmosphere to warm the Earth. So we thought that's a good thing. Okay? But when it goes into the ocean, the carbon dioxide dissolves in water. It mixes together and makes something called carbonic acid. Carbonic acid is an acid, and it splits apart and makes this little guy here, which we call hydronium ion, which is acid. But then there's still another one here, and that can split apart and make another one, and that can make carbonate. Now, carbonate for animals that make shells and plankton and stuff can be a good thing, but too much acid can actually drive it back the other way and dissolve shells. So that's a bad thing. Anyway, the balance of all this is in a scale that's, it's kind of foreign to us. They're just numbers. So 0 to 14 is called pH, and it's related to the concentration of these hydrogen atoms up here, hydrogen protons up here. And for the longest time, the oceans, say we go back to 1750 or so, the pH was 8.25. This doesn't mean anything to us. Okay, it's really the exponent, the negative exponent on the 10 to the power. So we're going to convert this to hydrogen ion concentration, which is a number. So this right here converts into 5.6 times 10 to the minus 9, they call it moles per liter. So we can just, since these are all 10 to the minus 9, we can kind of forget about these. We can just look at, this is the amount of acid. This is the amount of acid that we're looking at. And so over time, we've gone from 8.25 to 8.1. So that's about 250 years. We changed a little bit. So now the acid level is at about 7.2. So if we compare 7.2 to 5.6, like I did over here, that comes out to be about 1.29. We'll just say it's about 1.3. And so that means we're 29-30% more acidic. We have 29-30% more acid in the waters of the ocean. And you might say, well, okay, what does that mean? So I would say the ocean of the water is the fluid that all the life forms of the ocean live in, and we've just made it 30% more acidic. To give you a comparison, let's say we take the fluid inside of you, which is blood, and we make it 30% more acidic. I think we're going to die. Okay? If we make our blood 30% more acidic, our whole biochemistry breaks down, and it doesn't work. That's what we're doing to the ocean, and that's the air, the environment that all the animals and plants of the ocean live in. So it has a drastic effect. Now it's predicted that if we keep dumping carbon dioxide into the atmosphere the way we're doing, by the end of the century, we could lower the pH, we could increase the acidity to about 17 or even 25. So we could increase the acidity 300 times to 450%. Think about making your blood 300% more acidic, 3 times more acidic. You wouldn't live, you'd be dead. Okay, so this is a huge problem because the oceans mean a lot to us. Also, the oceans are warming, but they do it very slowly because of the high heat capacity. It takes a lot of energy to make the temperature go up, which is another thing that helps buffer the temperature increase of the Earth. Now, immediately, the most important concern most people are worried about is corals. So corals of the world are kind of special. They only occupy about 1% of the ocean. But on that 1%, they have about 25% of the ocean's diversity. They have a tremendous amount of life forms that live off of them. Now, the corals themselves, they have sort of a mutualistic relationship with the algae that's there. So there's algae that lives inside the little holes of the coral. And what the algae supplies is they supply the coral with oxygen and sugars, sort of like plants do for us. Okay, and in return, the corals supply the algae with some protection from things that want to eat them, and then the waste product of the corals become the food for the algae. So they kind of live together in a way that helps each other, kind of like you wish people would do. But unfortunately, the temperature increase and the acid increase affects these little algae guys. So they start to die off. They're already doing it. Like here is the Great Barrier Reef. So if you look at the Great Barrier Reef alive and you look at the Great Barrier Reef dead or bleached out, as they say, it's totally different. So, but anyway, if the algae start to die, then the coral starts to die. And if the coral starts to die, the reef diversity starts to die. And then kaput, we're done. Okay, and so that's happening around the world. And if we look at the oceans, we get a lot of our food from the oceans. Okay, we get a lot of stuff from the oceans. And if we look at the population, remember at the start, the population is shooting up. We're thinking 2-3 more billion people by the end of the century. So we can't have our food going down while the population are going up. Okay, we got to be smarter. So what do oceans give us? Life on Earth depends on the oceans. It's incredibly vast. It's 70% of our world. It absorbs a lot of the carbon dioxide. If all that went into the air, that would be harder for us to breathe. Okay, plus it's warming the atmosphere. So the oceans are helping us out there. People love the ocean. That's where most people live on the earth. So if you look around the earth, about 40% of the people worldwide live within 60 miles of the ocean. Okay, 40% of Americans live in counties directly on the shoreline. People love the ocean. Okay, in the ocean we have plankton, which undergo photosynthesis. They make carbon dioxide into oxygen and energy, carbohydrates. That's the base, the food base of the chain. It builds up all the life form above it. Human beings get about 25% of our protein from the ocean right now, and then we're talking, 2-3 more billion people in the coming decades. The oceans are critical to our survival, so we can't mess around with them. And that is what we're doing with the carbon dioxide that we're pumping into the environment. So I've heard a lot of people say we can grow our way out of this, so I just wanted to see. I did a little experiment here, so I'll take us through that. So we're getting close to being done. So I said, what's a really fast growing plant? Bamboo came to mind. They're one of the fastest growing plants. So I said, maybe we could grow bamboo so fast that it would take carbon dioxide out of the atmosphere and we could save ourselves. So the idealistic goal of my proposal is that we're going to take carbon dioxide levels from where they are now back to where they were in 1987, 350 parts per million. So now they're 415. We're going to reduce that 65 parts per million. So earlier I said that each part per million was 7.82 gigatons. So that means we have to remove 508 gigatons of carbon dioxide. Okay. Well, carbon dioxide is 40% carbon, and the molecule we're going to use for the bamboo is going to be cellulose, and that's about, sugar or cellulose is about 40% carbon, and carbon dioxide is about 27%. So that means we don't have to take quite as much carbon dioxide out to compensate for the sugar that we're growing, or the cellulose that we're growing. So we're going to reduce the amount of gigatons of carbon dioxide by about, we're going to reduce it by 1/3. So that means we only need to take out 338 gigatons. We have to make 338 gigatons of sugar, sorry for that, to equal that 508 gigatons of carbon dioxide. Now I'm going to assume that we grow the bamboo 20 feet tall. It takes about 4 years. We're going to assume they're about 2-inch canes in diameter, and we can assume we can plant about 200 of them per plants per hectare. Okay, and then we're going to assume that all the bamboo is cellulose, okay, which is 1.5 grams per cubic centimeter, and then we're going to assume bamboo is hollow, and so we're only going to take half of its cross-sectional area to be cellulose. Okay, so here we got a little bamboo plantation. So here's our little bamboo, diameter 4, radius is going to be 2 inches, which will be 5 centimeters. Bamboo is 20 feet tall, which will be 600 centimeters. So the area at the end is going to be about 314 square centimeters, but I'm going to take half of that because I'm assuming it's hollow. That'd be 157 square centimeters times the height times 600 centimeters. And that gives us a volume for that cane of bamboo of about 9,000 cubic centimeters. Okay, we need a mass from this. Okay, so the mass of a single bamboo cane, we're going to multiply each cubic centimeter by 1.5 grams. And so we come out with about 1.4 times 10 to the 4th grams. If I did pounds, that's about 31 pounds. If I did tons, that's about 0.0155 tons. Okay, because we're doing this on a large scale, because we're going to look at the entire carbon dioxide in the atmosphere. So if we took a whole hectare of canes, remember there's 200 of them, and each of them weighs about 0.0155 tons. So that means that whole hectare will give us 3.1 tons of bamboo. We're assuming it's all cellulose. Okay. Now the amount of carbon dioxide to be taken out of the atmosphere is 65 parts per million. So that was the 415 minus the 350 parts per million. 7.82 gigatons means we have 508 gigatons. We're going to reduce that down to around 340 gigatons. And so the amount of carbon dioxide we have to take out is 3.1 I took the giga, it's 10 to the ninth, times 10, 3 times 0.4 times 10 to the second. That's going to be 3.4 times 10 to the 11th tons of carbon dioxide to remove. Okay, so how many hectares do we need to do that? Okay, so here's the carbon dioxide we got to take out. And then we got to divide that by how many tons of cane per hectare. And there's only 3.1 tons of cane. And so that comes out to be 1.1 times 10 to the 11th hectares for all of that carbon dioxide. And so I put that into billions. So billion would be 10 to the ninth. So I have 110 billion, 10 to the ninth, hectares of bamboo to pull out all of that carbon dioxide. Well, what does that mean? Well, let's say the United States has 1,100 million hectares. Well, that's a million. That's only 1.1 billion hectares. If you look at the whole world, the world has 15,000 million hectares, but that's only 15 billion hectares. And we need 110 billion hectares. This is not going to work. Okay, we're coming up way short. Okay, we have 15 billion hectares available. We need 110 billion hectares. So that would mean wiping out every city, road, farmland, national park, and the bamboo would have to grow perfectly over every square inch, and it's not going to work. Okay. Also, we're pretending like we're not still dumping in 40 gigatons of carbon dioxide into the earth every year. So that's increasing the parts per million by about almost 3 parts per million every year. We're trying to suck out 65. That's 2 different directions. Okay. Another thing is, if we did pull it into the bamboo, we cannot let the bamboo decompose, because that would release the carbon dioxide back to the atmosphere. You know, that circle of life thing. So we would have to isolate all that bamboo for at least thousands of years to keep the carbon dioxide level down. This isn't going to work. Now, that doesn't mean that it's not good to plant trees and plants and allow them grow, because they do what we are not doing. Trees and bamboo and plants take carbon dioxide out of the atmosphere. Okay, we are dumping carbon dioxide into the atmosphere. So we need to do every little thing we can. So this is a matter of scale. And so we need to keep doing that, but we need to do other stuff too. Now, when I was looking at this, I noticed that somebody had already looked at seaweeds, because seaweeds are real fast growing. And somebody had considered this as a possibility to pull carbon dioxide out of the atmosphere. And then they said that you could digest that seaweed and use it as a replacement for natural gas, maybe make it into methane. They estimate that if you had seaweed farms that covered 9% of the ocean, now that's a lot of ocean, that's 6% of the earth. Remember, some of the ocean is like miles deep. They could produce enough biomethane to supply all Earth's equivalent demand for fossil fuels. Wow, that's a lot of fossil fuels. And they could remove 53 gigatons of carbon dioxide per year. Excuse me. And they could sustainably produce 200 kilograms per year of fish per person for 10 billion people. And this is like a dream. This is perfection. But there's a lot of buts here. How much energy would it take to plant all that? How would we get equipment out there to harvest it? How would we convert it into that energy? You know, there's a lot of stuff that we don't know here. This is just a thought experiment like I did above with the bamboo. So who knows? But we need to be trying ideas like this now. Okay, we are ignoring the problem and not doing anything about it. We need to be throwing everything we can at it. So I'm not going to go through all these. I'm just going to mention them. These are our possibilities. Our hope is in these things that we have here. Biomass. We have people converting corn and sugarcane into ethanol as a gasoline additive. The problem with that is it takes a lot of energy to do that, and the energy that we use to make it is about equal to the energy we get out of it. But it is a liquid form of energy that we could use, as opposed to, say, solar and wind and stuff. We have hydropower. Hydropower has been around forever, basically as long as people. Right now, about 2018, hydropower supplied 7% of the total electricity of the U.S. That's a lot of electricity. But the problem is we've kind of dammed up every big river around, so we don't have a lot of growth potential there. But still, this is a good source, and it's renewable. as long as we have water flowing. If the water changes, water patterns of the world change and we don't have the water flowing, then we got a problem. We have geothermal. It's real hot in places under the earth. We can pump down water, bring it up to the surface, run turbines that make electricity, pump it back down to the earth, into the earth, and cycle that over. So that's a possibility, but you got to be at just the right spot for that to happen. So that's not real general all over the world. Wind is really coming on. Okay, so now we have these giant windmills that can blow even not on land, they can blow out off into the ocean. So these have a few downsides, like they might kill some of the bigger birds, but life's going to die anyway if we don't do anything. So we got to do something, and some countries of the world have really pushed this and are really cranking. And we have potential by 2050 to make a significant dent. Right now, wind is cheaper than coal. We don't want to use coal. Coal is bad, dirty. Okay. We have solar energy. That's really big. A lot of people have solar on their houses. They can make electricity to run cars, to run factories, to run cities. Okay. We might need to change our grid structure for some of these, but that's something we need to be working on. Okay, the downside of solar is it only works when the sun's shining. I didn't mention it, but the downside of wind is it only works when the wind's blowing. However, if we can make nice big batteries that can store that energy, then we can pull on it when those things aren't working so well. So large storage batteries, this is something we need to be researching intensely, heavily. Okay, we need to do this. We're not doing it. Okay, hydrogen fuel cells. Again, these have a lot of potential. Right now, they're still struggling to make it sort of practical. States, California, Hawaii are using them. Japan and Germany are using things like this to help power cars. So there's a lot of possibility here. Maybe we could make every house have its own hydrogen generating system from water, and then every house could run on its own. But we don't know right now. It's too hard. Nuclear is kind of scary. Because there's so many downsides to radioactivity, but nuclear has been used for many decades, and it's very, very powerful. United States has most of the reactors, recently supplied 20% of our electricity. Okay, it doesn't really make carbon dioxide, and they're coming up with better and safer nuclear power plants. Okay, because there's really three names that make all of this really scary, and that's 3 Mile Island, Chernobyl, and Fukushima. Okay, these are all nuclear disasters that happen. So there's a real downside. But then you have to compare it to how many people die each year from using fossil fuels and pollution. It's not even close. Okay, fossil fuels kill way more people. Two other words that put the fear into nuclear is terrorism and waste. Okay, so the nuclear waste lasts for thousands of years, tens of thousands of years, and terrorism we just hope that never happens. So I think in the world that we're facing, in my point of view, we need to have nuclear power as sort of a bridge to get to another side where we have figured out how to use wind and solar and stuff. Energy conservation, okay, so we can all do something to try and be better. That's not going to solve our problem, but it will make us aware that there is a problem, and maybe make other people aware, and then maybe we can start to think of some of the stuff we have to do up here. Okay, so oftentimes they talk about mitigation. Mitigation is the act of lessening the force or intensity of something unpleasant. Okay, that's what we need to do. Okay, it's the act of making a condition or consequence less severe. So we need to look for things that mitigate the amount of carbon dioxide that we're putting into the atmosphere. Okay, so the big question is, how do we do it? They got people thinking about it, working on it, but we need everybody thinking about it, working on it. Okay, our efforts have been very feeble so far. One reason is they infringe on our really comfortable way of life. Okay, so we have to change. Okay, it's a really difficult thing to do. Mitigation, another problem is mitigation is a public good, but climate change is a case of what they call tragedy of the commons. Okay, it would be really good if all of us acted better and helped solve this problem. But what happens is a lot of us could act really good and help solve the problem. But some people say, well, I don't want to give up my Hummer. I don't want to give up flying to Europe every other week or something. Okay, they don't want to change something that has to be changed. And so what we need is a mechanism where we all act together. And so far that hasn't happened. That's probably the hardest thing about it. Then there's adaptation, where you change a process to make it better suited for its environment. This could be like a species evolving to live better in its environment. Okay, so what we need to do is we need to change the way we live, and so that might mean retreating back from the coastal areas that are going to get flooded. Okay, like think about Miami. They're building multi-story hotels and stuff right on the ocean, but maybe they shouldn't be doing that. Maybe we should be coming back to higher elevations, building walls to protect from encroachment of the sea. If you look at the Netherlands, they have protected themselves from the ocean rise for a long time, but they're coming into crunch time now because it's coming up too much. We have places like Bangladesh, so we need to do something to change that. Now, it's not the poor nations of the world that are going to do this. They don't have money. They're already getting the worst aspects of what's happening. It's the rich nations that need to cut back. Okay, and so it's really tough. Okay, do we either way we lose our complete? We have this indulgent, comfortable lifestyle, but that lifestyle cannot work for 10 billion people. Okay, so we need a balance. Some of us have to lower down what we're doing, and we have to allow the people at the very bottom to come up a little bit, so that we have a livable world in order to survive. Okay, so I have focused on mainly the energy aspects, a couple little side details, the ice melting, the bamboo and stuff. There's so many aspects that I didn't have time to cover. But all this is coming from increase of greenhouse gases. Okay, so what I'm hoping is that you're impressed, that you're alarmed at what we're doing and what potential we could still do. Okay, there are many scary consequences. They involve feedback cycles, say like we melt all the ice in Arctic, and now instead of albedo reflecting light back, we're absorbing the light, increasing the temperature. So there's plenty of things to look out there and see what's going on. You need to educate yourself. Okay, now a lot of people complain about Wikipedia, but Wikipedia I think is a great place to start. It doesn't cost money. It has reasonably balanced perspectives and detail that can get you started about what's going on. Okay, it talks about many of the alternatives that we can focus on. Okay, we need to be pouring money into research, pouring it in to come up with solutions for the problems we face. The problems we face are bigger than any problems we've ever faced. Okay, right now we are giving fossil fuel companies trillions of dollars in subsidies to continue undermining the future life on Earth. We need to stop that. No subsidies. In World War II, the United States spent about 40% of its gross domestic product, that's everything, on the war effort. Okay. Today's dollars, that's estimated at $4 trillion. Okay, they were spending to save ourselves in World War II. If we look at from 1993 to 2014, that's 20 years. We have spent $166 billion on climate change research. $166 billion. Okay, this problem is bigger than World War II. They were spending $4 trillion, 40% of their entire gross domestic product. Okay, so we're not even spending 0.1%. We need to change that. Okay, we're looking at every detail, every aspect. Okay, we need all of our scientists and engineers working on this. We owe it to the future generations of the world. Okay, it's up to us, and we need to do more. So this little curve right here is the Keeling curve. It started in the late 1950s. They started monitoring carbon dioxide. So for over 10,000 years, carbon dioxide had been at levels lower than 300. And now it's increasing up, 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 up. Okay, we need to change this curve. We can't let it keep going up. So I hope these slides have given you some reasons to and motivation to join in that cause. Because when you look at something like this, you got to ask yourself, is that the sunset or is that the sunrise? So I want to thank you for watching, and I hope you participate in solving this problem.